Space is everything that exists, has ever existed, and will ever exist. Just contemplating the cosmos is astounding. A shiver runs down your spine, your throat tightens, and you feel a sensation akin to a vague memory, as if you are falling from a great height. We realize we are touching the greatest mystery. The dimensions and age of the cosmos lie beyond normal human comprehension. Our tiny planetary home is lost somewhere between eternity and the vastness of space. In the face of the cosmos, most human endeavors seem insignificant, even empty. Yet the human race, being curious, brave, and full of hope, has made countless amazing and unexpected discoveries about the structure of the cosmos and our place within it over the past few thousand years. Reflecting on these discoveries is so captivating. They remind us that humanity is born to wonder, that understanding is a joy, and that knowledge is the key to survival. I believe our future depends on how well we understand this cosmos in which we drift like a speck of dust in the morning sky. These explorations require both skepticism and imagination. Imagination often takes us to unprecedented worlds, but without it, we would not get anywhere at all. Skepticism allows us to distinguish fantasies from facts and to test our assumptions. The cosmos is rich with immeasurably elegant facts, exquisite connections, and delicate organization that inspire a sense of awe. The surface of the Earth is the shore of the cosmic ocean. Almost all our knowledge has been gained without leaving it. Just recently, we stepped into the sea, wading in up to our ankles, at most up to our knees. The water beckons. The ocean calls us. Some part of our being knows that we came from there, and we are drawn to return. This longing, I believe, harbors nothing sacrilegious, although it may disturb all the gods that could possibly exist. The cosmos is so vast that it makes no sense to resort to such convenient earthly units of measurement as meters and kilometers to describe it. Instead, we measure distance in light years. In 1 second, a beam of light travels 300,000 kilometers, which is roughly equivalent to 7 laps around the Earth. In about 8 minutes, it covers the distance from the Sun to the Earth. We can say that the Sun is 8 light minutes away from us. In 1 year, light travels almost 10 trillion kilometers of cosmic space. The unit of length equal to the distance light travels in 1 year is called a light year, and it measures distance, not time. Gigantic distances. Earth is a special place, certainly not unique, but certainly not typical either. No planet, star, or galaxy can be typical because the cosmos is mostly empty. The only thing typical about it is the immeasurable icy universal vacuum, the eternal night of intergalactic space. A place so strange and desolate that in comparison, planets, stars, and galaxies seem like delightful exceptions. If we were to be randomly thrown somewhere in the cosmos, the chances of landing on the surface of a planet or near it would not exceed 1 in a billion trillion trillion. That is, 10 to the 33rd power. When written, this number appears as one followed by 33 zeros. In everyday life, such numbers are called astronomical. Planets are truly invaluable. From an observation post in intergalactic space, we would see a scattering of countless faint threads of light resembling sea foam on the waves of the cosmos. These are galaxies. Some of them are solitary wanderers, but most exist in communities, star clusters, and bunched together, drift endlessly amid the majestic darkness of the cosmos. Before us lies the cosmos on the largest scales known. We are in the realm of nebulae, 8 billion light-years from Earth, halfway to the boundaries of the universe as we know it. Each galaxy consists of gas, dust, and stars, billions and billions of stars. And each star may be something more than the sun. Within a galaxy, there are stars and planets, and the possibility of intelligent life from a cosmic civilization. But from a distance, galaxies remind me of a collection of lovingly gathered objects, shells, or perhaps corals, creations that nature has labored over in the cosmic ocean. There are whole galaxies, numbering several hundred billion, 10 to the 11th power, each consisting, on average, of 100 billion stars. In all galaxies combined, there seem to be roughly as many planets as there are stars. 10 to the 11th power multiplied by 10 to the 11th power equals 10 to the 22nd power, which is 10 billion trillion. In the face of such staggering numbers, what do you think is the probability that just one, the most ordinary star, our Sun, has a habitable planet? Why has this fortune befallen only us, lost in a remote corner of the cosmos? I find it much more likely that the cosmos is filled to the brim with life. We, humans, just do not know it yet. We are only beginning our explorations. From a distance of 8 billion light-years, it is difficult for us to even detect the cluster in which our galaxy, the Milky Way, is located, let alone the Sun and the Earth. The one planet we can be sure of being inhabited is just a tiny, rocky, metallic speck, a faint glimmer reflecting sunlight. And at such a distance, it would surely be lost from view. But now, our journey brings us to the local group of galaxies, as earthly astronomers call it. Spanning several million light-years across, it includes about 20 galaxies. This is quite a scattered, poor, and inconspicuous cluster. One of its galaxies, M31, is visible from Earth in the constellation Andromeda. Like other spiral galaxies, it is a vast disk of stars, gas, and dust. M31 has two small companions, two dwarf elliptical galaxies bound to it by gravitational attraction. Due to the same physical law that keeps me in my chair, the same laws of nature operate throughout the cosmos. And here we are now, 2 million light-years from home. Not far from M31 is another galaxy, very similar to it, our own. Its spiral arms rotate slowly, completing one revolution every quarter of a billion years. At 40,000 light-years from home, we find ourselves plunged into a fall toward the massive core of the Milky Way. But if we want to find Earth, we should change course and head toward the outskirts of the galaxy, to an inconspicuous spot near the edge of a distant spiral arm. Even between the spiral arms, we are accompanied by an exhilarating sight: stars racing by, an endless shining stream of the most diverse celestial bodies. Some are swollen like soap bubbles, and are so enormous that they could encompass tens of thousands of suns and trillions of planets. Others are the size of a small city and are 10 trillion times denser than lead. Some stars are solitary, like our Sun, but most have companions. Double systems are predominant, two stars orbiting each other. But this is not the limit. There is a smooth transition from embedded systems through small clusters containing several dozen stars to gigantic globular clusters sparkling with millions of suns. To date, no transitional forms between open and globular star clusters are known. These two types of clusters have significantly different origins. Some star pairs are so close that they nearly touch, and stellar material flows between their surfaces. However, for the most part, stars are separated from each other by distances roughly equivalent to that between Jupiter and the Sun. There are supernovae, whose brightness outshines entire galaxies. There are black holes so dense that they cannot be seen even from a few kilometers away. Although the black hole itself is invisible, it is noticeable nearby how its gravity distorts light rays, warping the view of the starry sky around it. Some stars have constant luminosity, while others flare unexpectedly or twinkle in an unchanging rhythm. Some rotate with leisurely grace, while others spin so flattened from the rotation. Most stars emit visible and infrared light, but there are also those that emit powerful streams of X-rays and radio waves. Blue stars are hot and young. Yellow ones are cooler and of middle age, while old and dying. Meanwhile, small white and black stars are on the brink of death. The Milky Way contains about 400 billion stars of all types moving in a complex and strict dance. But of all these, the inhabitants of Earth are currently only closely familiar with one. Each star system is an island in space, isolated from its neighboring ones by light years of emptiness. I can easily imagine how in countless worlds, living beings that have reached the first glimmers of knowledge through evolution initially consider their insignificant planet and the few modest suns to be everything. We ourselves grew up in isolation, gradually coming to understand. Some stars may be surrounded by millions of lifeless rocky debris, planetary systems that have stalled at an early stage of evolution. It is possible that many stars possess planetary systems very similar to giant ring gas planets on the periphery, icy moons, and closer to the center, small warm worlds shrouded in white-blue clouds. On some of these, intelligent life could have developed, transforming the surfaces of planets through intensive engineering activities. These are our cosmic brothers and sisters. How different are they from us? What are their chemistry, neurobiology, history, politics, science, technology, religion, and philosophy? Perhaps the day will come when we learn all this. For now, we are entering the courtyard of our home. 1 light year remains to Earth. The further approaches to the Sun are filled with giant snowballs and organic molecules which form a vast spherical mass. These are comet nuclei. Occasionally, a passing star gently nudges one of them into the inner regions of the solar system with a barely noticeable gravitational influence. There, the Sun heats the nucleus, causing the ice to vaporize and forming a beautiful comet tail. We are the largest world, the brilliant Sun, which with its gravity compels them to follow circular orbits and warms them with its radiation. Pluto, covered with a thin layer of ice and accompanied by is illuminated by the distant Sun, which appears no more than a bright sky. According to the New Horizons probe, which explored Pluto in 2015, the surface is predominantly nitrogen, 97 to 88%, with a small amount of methane. Important role in creating a greenhouse effect in Pluto's thin atmosphere. In 2006, the International Astronomical Union adopted a definition of a planet, by which a planet. By the characteristics of its orbit, it belongs to the category of trans-Neptunian objects, and by its spherical shape, it belongs to a new category of dwarf planets. Unlike larger planets, dwarf planets cannot clear their orbital neighborhood of competitors of comparable mass. A formal definition of a planet became necessary after the planets and trans-Neptunian objects. The Sun shines to 450 times brighter than a full moon. Brightness depends on the changing distance to the Sun. In such an uncertain state, Pluto's atmosphere, although hundreds of times less dense than Mars, from the surface the sky appears dim, taking on a blue hue with a layered haze. The giant gas planets Neptune, Uranus, and Saturn are the adornments of the solar system, while Jupiter is accompanied by a retinue of icy moons and a cloud of swirling icebergs. In the belt of gas planets, a central warm and rocky area of the solar system is found. Here, for example, lies Mars, with its towering volcanoes, gigantic rice valleys, monstrous planetary dust storms, and possibly some simple forms of life. All planets orbit the Sun, the closest star to us, a hydrogen-helium gas inferno where thermonuclear reactions fill the entire solar system with light. Finally, completing our journey, we return to the tiny, fragile, bluish-white world lost in the cosmic ocean, the dimensions of which surpass our boldest fantasies. This is just one of countless worlds. It is precious only to us, Earth, our home, our ancestral mother. Here, life of our kind arose and developed. Here, after many centuries, the human species appeared. It is in this world that our passion for exploring the cosmos was born, and it is here that we build, sometimes in agony and without any guarantees, our destiny. Do you know the statutes of the sky? Can you establish its dominion on earth? The Book of Job, chapter 38, verse 33. All the good and evil that happens to people and other creations occurs due to the 7 planets and the 12 signs of the zodiac. And those 12 constellations, as it is said, behave like 12 with victories on the side of Ormuzd the light, and the 7 planets, 7 with victories on the side of Ahriman the darkness. And the 7 planets conquer all creations and beings and doom them to death and all evil. So, the 12 constellations and the 7 planets create the world and govern it. Dagestan and Minog are pleased with their judgment, the spirit of wisdom. The late Zoroastrian book speaks of how each kind of thing is endowed with special hidden qualities that determine their behavior and observable effects. This means saying nothing, but deriving 2 or 3 general principles of motion from observable phenomena, and then explaining how the properties and behaviors of all material things arise from these obvious principles. This would be a significant achievement. To say that each kind of thing is endowed with a special hidden quality through which it acts and produces apparent effects means saying nothing. But deriving 2 or 3 general principles of motion from phenomena, and then explaining how the properties and actions of all physical things arise from these apparent principles would be a very important step. Isaac Newton, Optics. We do not ask what the benefit of birds singing is, since, being created for singing, they find pleasure in it. Similarly, we should not ask why the human mind strives to unravel the secrets of the heavens. The variety of natural phenomena is so vast, and the treasures hidden in the heavens are so rich, that people will never lack fresh food for thought. Johannes Kepler, The Secret of the Cosmos. If we lived on a planet where nothing ever changed, we would have nothing to do, nothing to imagine, and no impulses to give rise to science. And if we were in an unpredictable reality, where everything changes randomly or in very complex ways, we would not be able to adequately judge things. And once again, science would be impossible. However, we live in an intermediate world where things change, but according to certain schemes, rules, or, as we call them, laws of nature. If I throw a stick up, it will always fall down. If the sun sets in the west, it will always rise again in the east the next morning. All this allows us to form an understanding of things. We can create science and use it to improve our lives. Human beings have been very successful in understanding the world. It has always been so. We succeeded in hunting and making fire only because we managed to understand something. There was a time before television, before cinema, before radio, before books. Most of human existence falls in the time when we sat by the smoldering embers of a campfire. Under moonlit nights, we watched the stars. The night sky captured our attention. Patterns emerged on it. With little effort, you can guess at their images. In the northern sky, for example, there is a figure or constellation that resembles something bear-like. In some cultures, it has been named the Great Bear, while others saw entirely different images. Of course, in reality, none of these images exist in the night sky. We placed them there ourselves. We were hunters, and therefore saw hunters and dogs, bears, and young women, all that captured our interest. When European sailors first gazed at the southern sky, in the 17th century, they placed on it objects that occupied minds in that era. So it was with the peacock, the telescope and microscope, the compass, and the ship's stern. If constellations were named in the 20th century, I believe bicycles and refrigerators, rock and roll stars, and possible mushroom-shaped clouds would have been seen, a new set of human hopes and fears placed among the stars. Sometimes our ancestors noticed a very bright star with a tail that crossed the sky in the blink of an eye. They called it a falling star, not the most fortunate name, as all the old lights remained in their places after the meteor passed. Certain times of the year were rich in falling stars, while at others there were very few. There was some regularity there. Like the sun and the moon, stars always rise in the east and set in the west, taking a whole night to cross the sky above our heads. Different constellations are visible at different times of the year. For example, at the beginning of autumn, the same groups of stars always rise. It has never happened that a new constellation suddenly appeared in the east. Order, predictability, and permanence reign among the stars. In a certain sense, this is comforting. Depending on the season, certain stars rise above the horizon just before dawn and set right after sunset. If one carefully observes the stars and records the results over many years, one can learn to predict the arrival of the seasons. The time of year can also be determined by noting each day where the sun rises on the horizon. The sky is a great calendar, accessible to anyone willing and able to understand it, and who has the means to keep records. Our ancestors built special structures to predict the change of seasons. In Chaco Canyon, New Mexico, a huge ceremonial kiva, an open-air temple dating back to the 11th century, was erected. On the longest day of the year, June 21st, a ray of sunlight penetrates through a window at dawn and slowly moves along a specially made niche. But this only happens near June 21st. I can imagine how proud the people of the Anasazi tribe, who called themselves the Ancients, dressed in feathers, rattles, and turquoise, gathered in the temple on June 21st to catch the power of the sun. They also observed the visible movement of the moon. The 28 upper niches in the kiva may correspond to the number of days it takes for the moon to return to its previous position among the constellations. This people paid great attention to the sun, the moon, and the stars. Structures based on the fundamental principles found in Angkor Wat in Cambodia, Stonehenge in England, Abu Simbel in Egypt, Chichen Itza in Mexico, and the Great Plains of North America could be mistakenly counted as ancient observatories. By pure coincidence, the window is positioned such that on June 21st, light from it falls into the niche. But there are also other devices of a completely different nature. In the southwestern United States, a structure made of 3 vertical stone slabs, moved from their natural position about 1,000 years ago, has been discovered. A spiral is carved into the rock, vaguely resembling a galaxy. On June 21st, the first day of astronomical summer, a shining blade of sunlight, penetrating through the gap between the slabs, bisects the spiral exactly in half. While on December 21st, the first day of astronomical winter, 2 rays of sunlight converge precisely at the sides of the spiral. This is a unique example of using the midday sun to read a celestial calendar. Why do people around the world expend so much effort studying astronomy? We hunted gazelles, antelopes, and buffalo. Their migrations were determined by the change of seasons. Fruits and nuts ripened at specific times. With the advent of agriculture, we needed to tend to plants and harvest according to the seasons. Annual meetings of nomadic tribes were scheduled for predetermined times. The ability to read the celestial calendar was literally a matter of life and death. The appearance of the lunar crescent following the new moon, the return of the sun after a total eclipse, its morning rise after a troubling night absence were noted by people around the world. These phenomena convinced our ancestors of the possibility of surviving death. Thus, the heavens gradually became a symbol of immortality. There will be wind in the canyons of the American Southwest, but no one but us will hear in it the reminder of 40,000 generations of thinking men and women who lived before us, of whom we know nothing, but who laid the foundations of our civilization. For centuries, people have inherited the experiences of their ancestors. The more accurately you know the position and movement of the sun, the moon, and the stars, the more reliably you can predict when to hunt, when to sow and reap, and when to gather tribes. With increasing measurement precision, it became necessary to keep records. Thus, astronomy contributed to the development of observation, mathematics, and writing. But then, much later, other rather strange ideas began to emerge. An invasion of mysticism and superstition occurred in the realm of predominantly empirical science. The sun and stars governed the change of seasons. They determined food and warmth. The moon controlled tides and the life cycle of many animals. There were other celestial bodies, wandering or errant stars, planets. Our nomadic ancestors must have felt their connection to them, aside from the sun and moon. Only 5 planets could be seen. They moved against the backdrop of more distant stars, and if you tracked their visible movements over many months, you could notice how they transitioned from one constellation to another, sometimes even describing a kind of dead loop in the sky. All celestial phenomena exerted some influence on human life. What should be the influence of the planets today? In the West, you can buy an astrological magazine at any kiosk. It is much harder to find a publication on astronomy. Practically every American newspaper has a daily astrology column, but it is unlikely that there is one that dedicates even a single column a week to astronomy. In the United States, there are 10 times more astrologers than astronomers. When I meet people at parties who do not know that I am a scientist, I often hear, "Am I by any chance a Gemini?" Or, "What's your sign?" Much less frequently am I asked, "Did you hear that gold formed in a supernova explosion?" Or, "When will Congress approve the Mars rover project?" Astrology claims that the constellation in which the planets were located at the moment of your birth leaves an indelible mark on your entire future. The idea that the movement of planets governs the fate of kings, dynasties, and empires originated several thousand years ago. Astrologers studied the course of celestial bodies and wondered what happened the last time. For example, Venus was in the constellation Capricorn. Perhaps something similar will happen again. This was a clever and quite risky venture. It came to the point where astrologers were kept exclusively in government service. In many countries, interpreting celestial omens was considered a serious crime for everyone except court astrologers. To overthrow a regime, it was sometimes enough to predict its fall. In China, court astrologers were executed for inaccurate predictions. Their fellow craftsmen would adjust records to ensure that prophecies aligned with the course of events. Astrology developed into a strange combination of observations, mathematics, and meticulous record-keeping with lightweight thinking and deception. But if planets can determine the fate of a nation, can they not influence what will happen to me tomorrow? The fundamental concepts of individual astrology were formed in Hellenistic Egypt and spread throughout the Greco-Roman world about 2,000 years ago. Today, we can feel the antiquity of astrology through words like disaster, which in Greek means bad star, or influence, which in Italian literally means the influence of stars. The Hebrew mazal tov, good luck, has Babylonian roots and translates as good constellations. The word shlimazel, which a Yiddish speaker uses to refer to a fatally unlucky individual, also traces back to Babylonian astronomical lexicon. According to Pliny, the Romans perceived the word federation as the revenge of a planet. It was common to see planets as the immediate cause of people's deaths, or at least the word consensus, in agreement with the planets, which obviously suggests serious contemplation. John Grant compiled mortality statistics in the city of London in the 16th year against the backdrop of terrible losses from infant and childhood diseases, as well as exotic ailments like lung congestion and royal disease. We find that, out of 9,053 deceased, 13 fell victim to planets, more than died of cancer. It is interesting to consider what the symptoms were. Individual astrology exists even today. Let's consider the astrological columns published in the same city on the same day by two newspapers. For example, take the New York Post and the Daily News from September 21st, 1979. Suppose your sign is Libra, meaning you were born between September 23rd and October 20th. The astrologer in the Post writes, "A compromise will allow you to ease tensions." Reasonable, perhaps, but somewhat vague. On the same day, the astrologer from the Daily News urges you to demand more from yourself, a recommendation of a different kind, but equally vague. These predictions are not predictions at all. They are more like fragmented advice on what one should do, rather than what is supposed to happen. They are intentionally phrased so that they can apply to anyone, and at the same time, they demonstrate complete mutual incompatibility. Why are they published without any reservations, like sports results or stock market summaries? Astrology can be tested on the fates of twins. There are numerous cases where one twin died in childhood, for example, falling from a horse or being struck by lightning, while the other lived to old age. Both were born in the same place with only a few minutes apart. The planets were in the same position at their birth. If we assume that astrology is correct, how is it that twins experience such different fates? It happens that even among themselves, astrologers cannot agree on the meaning of a particular horoscope. Careful examination shows that they are unable to predict the character and future of people about whom they know nothing except the time and place of birth. There is something curious about national flags. The flag of the United States features 50 stars, while the flag of Burma has 14, Grenada and Venezuela have 7 each, China has 5, and Iraq has 3. The flags of Japan, Uruguay, Malawi, Bangladesh, and Taiwan depict the sun. Brazil's flag is adorned with a depiction of the celestial sphere. Australia, Western Samoa, New Zealand, and Papua New Guinea feature the constellation of the Southern Cross on their flags. Bhutan has a dragon with a pearl, symbolizing the earth. Cambodia is represented by the Astronomical Observatory of Angkor Wat. India and South Korea display cosmological symbols. States depict stars on their flags. Many Islamic flags feature a crescent moon. And much has changed. The names and state symbols of several countries that once belonged to the socialist camp have changed. The term 1989 refers to Myanmar. Its flag has 1 star. The flag of Venezuela has had 8 stars since 2006. On the Iraqi flag, the stars have been replaced with the inscription Allah Akbar. Western Samoa has simply been called Samoa since 1997. The Temple of Angkor Wat can only be very loosely termed an observatory. Almost half of national flags feature astronomical symbols. This is a global, transcultural, interfaith phenomenon that is not limited to our time. The constellation has been associated with length and the cylindrical seals of the Sumerians from the 3rd millennium BCE and the wax banners of pre-revolutionary China undoubtedly indicate the desire of peoples to connect with the power and stability of the heavens. We seek connections with the cosmos, wanting to be part of its grand scale, and it turns out that we are indeed connected to it, but not in a personal or primitive way, as astrologers suggest. Rather, on a profound level that touches on the origins of matter, the habitability of Earth, evolution, and the fate of humankind, topics to which we will return. Modern popular astrology originates from Claudius Ptolemy, whom we simply call Ptolemy, although he was not related to the royal dynasty of the same name. He worked in the Library of Alexandria in the 2nd century. All these mysterious discussions about planets rising in our solar and lunar houses, about the age of Aquarius, began with Ptolemy, who codified the Babylonian astrological tradition. Here is a typical horoscope from the time of Ptolemy, recorded on papyrus in Greek, for a girl born in the year 151 of the birth of Philus and the 10th year of Emperor Antoninus's reign. The night from the 15th to the 16th of month X, minus 1 hour past midnight. The reign of Emperor Antoninus Pius lasted from 130 to 161. The night from the 15th to the 16th of the month, Aminos according to the Egyptian calendar. The Sun in Pisces, Jupiter and Mercury in Aries, Saturn in Cancer, Mars in Leo, Venus and the Moon in Aquarius, under the sign of Capricorn. Even the methods of counting years and months have changed over the centuries more than the nuances of astrological vocabulary. A characteristic excerpt from the astrological treatise 3 Meters of Byblos states, "If Saturn is in the east, he makes his subjects dark-skinned, strong, black-haired, and curly, endowing them with hairy chests, medium-sized eyes, average height, and a temperament determined by an excess of wet and cold." According to Aristotle, all things possess 4 basic qualities: cold, heat, dryness, and wetness, the degree of which determines everything, including human temperament. Ptolemy believed that not only behavior, but also height, physique, national character, and even congenital physical defects are determined by the stars. In this respect, modern astrology takes a more cautious stance. However, contemporary astrologers have forgotten about the phenomenon of precession, which Ptolemy knew, ignore atmospheric refraction, which he wrote about, and pay little attention to all the satellites and planets, asteroids, comets, quasars, pulsars, exploding galaxies, symbiotic stars, cataclysmic variables, and X-ray sources that have been discovered since Ptolemy's time. To lend scientific credibility to their activities, Some astrologers use the most precise ephemeris calculation programs and the latest astronomical data, including information about exotic cosmic objects. However, this does not make astrology a science, as it lacks the fundamental scientific cycle of hypothesis formulation and repeated experimental verification. Astronomy is the science that studies the universe as it is, while astrology is a pseudoscience that, in the absence of convincing evidence, claims that planets influence our daily lives. In Ptolemy's time, the distinction between astronomy and astrology was not clearly defined. Now it is obvious. As an astronomer, Ptolemy named stars and assessed their brightness, provided convincing arguments for the spherical shape of the Earth, developed rules for predicting eclipses, and, perhaps most importantly, attempted to explain why the motion of planets against the backdrop of distant constellations appears so strange. Ptolemy's fundamental astronomical work, the Almagest, includes an expanded star catalog by Hipparchus. To understand the motion of planets and decode celestial messages, he developed a model with predictive power. Studying the sky brought Ptolemy to ecstasy. "Like all mortals," he wrote, "I know that I was born on a day, but when I follow in my thoughts the orderly ranks of countless stars in their circular motion, my feet no longer touch the ground." This quote is often mistakenly attributed to the Almagest. In reality, it is known from a Latin anthology, a collection of ancient and medieval Greek epigrams compiled in the 10th century in Byzantium. Ptolemy believed that the Earth is the center of the universe, with the sun, moon, planets, and stars moving around it. This is the most natural worldview. The Earth seems stable, solid, and motionless, while celestial bodies, by our observations, rise and set daily. All cultures have gone through the geocentric hypothesis. As Johannes Kepler wrote, it is utterly impossible for an untrained mind to imagine that the Earth is anything other than the mouth of a vast structure crowned by the dome of the sky. It is motionless, while within it the sun, so small, moves from one region to another, much like birds travel through the air. But how can we explain the visible movements of planets, such as Mars, which were known 1,000 years before Ptolemy? One of the epithets the ancient Egyptians gave to Mars was CDT-FM hit, which meant the one that moves backward. This is a clear indication of retrograde motion when a planet makes a dead loop in the sky. Ptolemy's model of planetary motion can be illustrated using a small machine, similar to one that actually existed in his time. 4 centuries earlier, such a device was constructed by Archimedes and described by Sura. The latter studied the machine in Rome, where it was brought by the Roman general Marcellus, and during the siege of Syracuse, without any reason, against orders, killed Archimedes, who was already over 70 years old. The task was to find such true observations as being from above, from the outside, the motion of planets that would accurately reproduce the visible paths of planets traced from below, from the inside. It was believed that planets move around the Earth, being attached to perfect transparent spheres. However, they were not directly attached, but rather through small rotating wheels with centers on the spheres. The sphere turns, the small wheel rotates, and we on Earth see Mars making its looping movements. This model allowed for the prediction of planetary motion with sufficient accuracy given the precision of measurements achievable in Ptolemy's time and even many centuries later. Because in the Middle Ages, Ptolemy's etheric spheres were regarded as crystalline, we still talk about the music of the spheres and the seventh heaven. One sphere, or heaven, was assigned to the moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn, while another was designated for the stars. When the Earth is the center of the universe, when the cosmos revolves around earthly events, and the heavens are arranged according to completely unearthly principles, there is little reason for conducting astronomical observations. Supported by the Church in the early Middle Ages, Ptolemy's model delayed the development of astronomy for an entire millennium. Only in 1543 did the Polish canon Nicholas Copernicus publish a completely different hypothesis explaining the visible movements of planets. The boldest aspect of it was the suggestion that the Sun, not the Earth, is at the center of the universe. The Earth was relegated to the status of an ordinary planet, the third from the Sun, moving around it in a perfect circular orbit. Ptolemy mentions such a heliocentric model, but immediately rejects it. From Aristotle's perspective, the implied wild rotation of the Earth contradicts observations. Not only the power, sanctified by centuries of tradition, but also observations did not allow for a clear choice in favor of Copernicus's teachings. His theory, based on the hypothesis of islands, circular, and uniform motion of planets, did not allow for predicting their visible movements with the same accuracy as Ptolemy's model, which was based on a complex system of deferents and epicycles. The only advantage of Copernicus's worldview at that time was that it was simpler and more logical. Recently, while inventorying all copies of Copernicus's book made in the 16th century, I concluded that censorship was ineffective. Only 60% of copies in Italy were corrected, and among those, none were found. The new theory explained the visible movements of planets at least as well as Ptolemy's spheres, yet it irritated many. In 1616, the Catholic Church placed Copernicus's work on the list of prohibited books until it was corrected by a local church censor, where it remained until 1835. Martin Luther remarked about Copernicus, "An upstart, an astrologer. He is a fool who wants to overturn all astronomical science. Yet the Holy Scripture tells us that Jesus commanded the sun to stand still, not the earth." Even some supporters of Copernicus said that he did not actually believe in a heliocentric universe, but merely proposed a hypothesis convenient for calculating planetary motion. The epical confrontation between two views of the cosmos, the geocentric and heliocentric, reached its climax in the 16th and 17th centuries, and was embodied in the person of a man who, like Ptolemy, was both an astrologer and an astronomer. He lived in a time when the human spirit was in chains, and reason was shackled, when millennia-old judgments of the Church Fathers on scientific matters were placed above the latest discoveries made using methods unavailable in antiquity, when deviations from Catholic and Protestant dogmas, even in obscure theological issues, were punished with humiliation, fines, exile, torture, and death. The heavens were populated with angels and demons, and the right hand of the Lord set the crystalline planetary spheres in motion. Science had not yet embraced the idea that the laws of physics underlie natural phenomena, but the courage of this struggling man was destined to ignite the first spark of the modern scientific revolution. Johannes Kepler was born in Germany in 1057 and was sent as a child to a Protestant seminary in the provincial town of Maulbronn to study to become a priest. It was a sort of boot camp for recruits, where young minds learned to wield logical weapons against the fortress of Roman Catholicism. Kepler, stubborn, intelligent, fierce, and independent, spent 2 lonely years in dreary Maulbronn, becoming detached and withdrawn, focused on his imagined insignificance in the eyes of God. He swore to thousands of sins, though he was no worse than others, and feared he would never attain salvation. But God became something more to him than a heavenly wrath demanding appeasement. The God of Kepler was the creative force of the cosmos. The boy's curiosity triumphed over fear. He wanted to study universal eschatology and dared to contemplate divine providence. These dangerous thoughts, initially insignificant, later became the meaning of his entire life. The bold aspirations of the seminarian child contributed to Europe's liberation from the confines of medieval thinking. For over 1,000 years, classical ancient science had been silenced, yet at the end of the Middle Ages, a faint echo of their voices, picked up by Arab scholars, began to penetrate European curricula. In Maulbronn, Kepler heard these echoes, studying ethnology, Greek and Latin languages, music, and mathematics. In Euclidean geometry, he saw a glimpse of perfection and cosmic beauty. Later he wrote, "Geometry existed before creation. It is as eternal as divine providence. Geometry gave God a model for creation. Geometry is God himself." Not even his absorption in mathematics or his ascetic lifestyle protected Kepler from the imperfections of the surrounding world, which left its mark on his character. At that time, superstitions served as a panacea for people too weak to withstand misfortunes, famine, and deadly religious wars. For many, the only unshakable thing remained the stars, and ancient astrological speculations thrived both at royal courts and in taverns haunted by Europe's fears. Kepler remained ambiguous in his attitude towards astrology throughout his life, striving to understand whether hidden patterns underlie the chaos of everyday life. If the world was created by God, should we not study it as thoroughly as possible? Is not everything created an expression of the harmony of divine providence? The book of nature had awaited its reader for over 1,000 years. In 1589, Kepler left Maulbronn to study theology at the famous University of Tübingen, and this became a liberation for him. His genius, which opposed most of the significant intellectual currents of the time, was immediately noticed by his teachers, one of whom introduced the young man to the dangerous secret of Copernicus's hypothesis. The heliocentric model resonated with Kepler's religious feelings and was embraced by him with enthusiasm. The sun embodied God, around which everything else revolved. Even before his ordination, Kepler was offered a very attractive secular position, which he, perhaps due to indifference to a church career, deemed suitable for himself. He went to the Austrian city of Graz to teach mathematics to schoolchildren, and shortly thereafter began preparing astronomical and meteorological calendars and composing horoscopes. For every creature, God has provided means of sustenance, Kepler wrote. For the astronomer, he prepared astrology. Kepler was a brilliant thinker and articulated his thoughts clearly on paper, but he proved to be a complete disaster as a schoolteacher. He mumbled, got distracted, and what he said was sometimes completely incomprehensible. In his first year in Graz, he managed to gather only a handful of students. The following year, no one came to him. Unceasingly, my internal chorus of associations and reflections constantly distracted him from the subject, competing for his attention. One fine summer day, thoroughly mired in the thickets of an endless lecture, he suddenly experienced a revelation that was to radically change the future of astronomy. Perhaps he paused mid-sentence. His inattentive students eagerly awaited the end of the day, having dozed off. I think this was a historical moment. In Kepler's time, only 6 planets were known: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Kepler wondered, why only 6? Why not 12 or 100? Why are the distances between their orbits exactly as defined by Copernicus? No one before him had asked such questions. Even in the time of Pythagoras, 5 perfect Platonic solids were known: polyhedra, whose faces are regular polygons. Kepler's thought was that these 2 numbers are related, that the reason for the existence of only 6 planets lies in the presence of only 5 perfect solids, and that these solids, being inscribed or nested within each other, would give us the distances of the planets from the Sun. Kepler believed that in these perfect forms he had discovered an invisible structure supporting the spheres of the 6 planets. He called his revelation the cosmographic secret. The book Mysterium Cosmographicum, published in 1596, was Kepler's first major work on astronomy. In Russian, it is also known as The Secret of the Universe and The Secret of Creation. The connection between Platonic solids and the arrangement of planets could have only one explanation. It is the right hand of God. Kepler was astonished by his geometry. It was he, mired in what he thought were sins, who was chosen for the highest purpose of making a great discovery. He approached Duke Württemberg with a request for funding for research, proposing to test the construction of nested polyhedra by creating a 3-dimensional model that would allow others to grasp the beauty of sacred geometry. His model, according to Kepler, could be made of silver and precious stones, and, among other things, serve the Duke as a cup. The proposal was declined, accompanied by the kind advice to first create a less expensive model out of paper, which Kepler attempted to do. The pleasure I derived from this discovery is beyond words. I was not daunted by the complexity of the calculations or anything else. Days and nights I spent in mathematical labors to ascertain whether my hypothesis would align with Copernicus's, or whether my joy would dissipate into thin air. But no matter how hard he tried, Kepler could not establish a correspondence between the polyhedra and the orbits. Nevertheless, the beauty and grandeur of the theory inclined him to conclude that errors had crept into the observations. This conclusion is not new in the history of science. Many theorists have arrived at it when their concepts did not align with experience. At that time, there was only one person in the world who had access to more accurate observations of the visible positions of planets: the Danish nobleman Tycho Brahe, who had taken the post of imperial mathematician at the court of Rudolf II, Emperor of the Holy Roman Empire. It so happened that at Rudolf's suggestion, he invited Kepler to join him, and the weak mathematician grew stronger, joining him in his labors. In Prague, a provincial teacher, a man of low birth, unknown to anyone except a few mathematicians, Kepler hesitated to accept this invitation, but everything was decided for him. In 1598, he was affected by one of the first shocks of the impending 30 Years' War. The local Catholic archduke, firmly adhering to the dogmas of faith, swore that he would rather devastate the country than rule over heretics. This was far from the most radical statement of the medieval and Reformation times. When Dominic de Guzman, later canonized and named Saint Dominic, was asked during the siege of a large city how to distinguish a true believer from a pagan, he reportedly replied, "Kill them all. The Lord will know his own." This phrase is mentioned by Caesar Geist, to whom, 20 years after the events described, the author attributes these words to the papal legate Arnold. Gradually, it is unknown whether they were actually spoken, though the brutality of the massacre at Béziers, which began the bitter alibi of the crusade, certainly corresponds to it. Protestants were cut off from economic and political power. The school where Kepler taught was closed. Prayers, books, and songs deemed heretical were banned. To top it all off, townspeople were subjected to interrogations about their religious beliefs. Those who refused to accept the Roman Catholic faith were punished by losing a tenth of their income and were to leave the town forever under the threat of death. Kepler preferred exile to hypocrisy. "I am untrained. I am serious about matters of faith. I do not play with this." Leaving the town, Kepler, his wife, and stepdaughter embarked on a difficult journey to Prague. Kepler was not happy in his marriage. His wife, who was often ill and had lost 2 small children, was described as dull, gloomy, withdrawn, and morose. She had no idea what her husband was working on, and having been raised in a petty noble environment, despised her husband's low-income occupation. He, in turn, would either admonish or ignore her, as, "My research sometimes made me careless." But I learned my lesson. I learned to remain calm with her when I saw that she took my words to heart. I would rather bite you on the finger than cause her another offense. Despite all this, Kepler was completely absorbed in his work, and Tycho Brahe seemed to him a refuge from all the evils of the time, a place where his secret of the universe would be welcomed. He dreamed of becoming an associate of the great scientist who had devoted 35 years to meticulously ordered and precise measurements of the cosmic clockwork before the invention of the telescope. Kepler's expectations were not destined to be fulfilled. Tycho Brahe turned out to be an extravagant figure. He sported a golden nose, having lost his own in a student duel for the title of the best mathematician. Around him was always a pack of boisterous sycophants, hangers-on, poor relatives, and other leeches. Their endless feasting, slander, and schemes, their cruel mockery of the pious and diligent provincial simpleton, oppressed and saddened Kepler. Tycho was incredibly wealthy, but did not know how to use his wealth. Each of his instruments cost more than what I owned, along with my entire family. Kepler was eager to see Tycho Brahe's astronomical data, but he only occasionally tossed him some rough drafts. Tycho does not give me the opportunity to make use of his results. Only sometimes at a feast or in passing does he suddenly mention that today one planet passed apogee, tomorrow another will be at the node. Tycho performed the best observations. He had assistants, but he lacked architects who could organize his results. Tycho Brahe was the greatest observer of his era, while Kepler was the greatest theorist. Everyone knew that alone they could not achieve a synthesis and build an accurate and coherent system of the world, which both felt was already on the horizon. But Tycho was unwilling to present the labor of his life as a gift to a potential young rival. Joint authorship was unacceptable for a number of reasons. The birth of modern science, the fruit of theory and experimentation, was threatened by mutual distrust. For all 18 months that Tycho had left to live, the two quarreled and reconciled. At a dinner at Baron Rosenberg's, Tycho drank a lot of wine, placing politeness above health and resisting natural urges, did not even briefly leave the table before the host. The subsequent inflammation of the bladder led to complications. When Tycho resolutely refused to limit his food and drink, on his deathbed, he bequeathed all his observations to Kepler, and on the last night, in delirium, he repeatedly recited, as if composing poetry, "Let me not feel that life has been lived in vain. Let me not feel that life has been lived in vain." After Tycho Brahe's death, Kepler, having become the court mathematician, managed to demand the observation diaries from the quarrelsome family of the deceased. His conjecture that the orbits of planets are described by the 5 Platonic solids was not confirmed by Tycho's data, nor by Copernicus's. Ultimately, the mystery of the universe was disproven much later when the planets Uranus, Neptune, and Pluto were discovered, as there are no other Platonic solids that could set their distances from the Sun. Moreover, the nested Platonic solids did not account for the existence of the Moon, nor for the 4 large moons of Jupiter discovered by Galileo. But Kepler did not fall into despair. On the contrary, he wanted new satellites to be found for the planets and pondered how many satellites each planet should have. He wrote to Galileo, "I immediately began to think about how to increase the number of planets without abandoning my secret universe, according to which the 5 perfect solids of Euclid do not allow more than 6 planets to revolve around the Sun. I am so far from disbelieving in the existence of the 4 moons revolving around Jupiter that I cannot wait to get a telescope to outpace you if I manage to discover 2 moons around Mars, as well as, it seems, requires the proportion of 6 or 8 around Saturn and possibly 1 each around Mercury and Venus. Mars, indeed, has 2 small moons and a large geological formation on one of them, now named the Kepler Ridge in honor of this conjecture. However, regarding Saturn and Mercury with Venus, Kepler was mistaken, and Jupiter, as it turned out, has many more moons than Galileo discovered. Finally, in 2018, over 70 moons were already discovered around Jupiter, one of the 4 discovered by Galileo in 1610 using the telescope he invented. Over 3.5 centuries, ground observations allowed the number of known moons to reach 12. 4 more moons were discovered by Jerome starting in 1999. The discovery of moons around large planets has effectively become routine. The recently discovered moons are very small, and their sizes do not exceed a few kilometers. It is quite possible that these are asteroids captured by Jupiter. In reality, we still do not know why there are exactly 9 planets, no more, no less, and why their distances from the Sun are exactly as they are. Listen to Chapter 8. Tycho Brahe's observations of the visible motion of Mars and other planets against the backdrop of constellations spanned many years. This data, collected over several decades before the invention of the telescope, was more accurate than any obtained before. Kepler, striving to understand them, worked with fierce dedication. How do the real motions of Earth and Mars around the Sun explain the precise measurements of the visible positions of Mars in the sky, including loops and retrograde motion against the stars? Tycho pointed out to Kepler to pay special attention to Mars, as the visible movements of this planet appeared the strangest and least consistent with circular orbits. Addressing the reader, who might have grown weary of his cumbersome calculations, he wrote, "If this tedious procedure has exhausted your patience, be lenient towards the one who has done this no less than 70 times. Pythagoras in the 6th century BCE, Plato, Ptolemy, and all Christian astronomers before Kepler assumed that planets moved in circular paths. The circle was considered the perfect geometric figure, and planets, residing in celestial heights far from earthly filth, were also perceived as perfect in a mystical sense. In uniform, circular motion of planets believed both Galileo and Tycho Brahe, and Copernicus, the latter asserting that it would be contrary to our reason to suppose anything else in what is arranged in the best order. Therefore, initially, Kepler tried to interpret observations by representing Earth and Mars moving in circular orbits around the Sun. After 3 years of calculations, he was convinced that he had found the correct characteristics of Mars's circular orbit, which matched Tycho's 10 observations with an accuracy of 2 arc minutes. Recall that 60 arc minutes make 1 degree, and 90 degrees is a right angle, for example, the angle from the horizon to the zenith. So, a couple of arc minutes is a very small amount for measurement, especially without a telescope. This is about 1/15 of the angular size of the visible Earth, a full moon. However, the joy that filled Kepler soon turned to despair. The next 2 observations by Tycho were incompatible with Kepler's orbits, and the difference reached 8 arc minutes. Divine Providence sent us Tycho Brahe, such a diligent observer that if his observations indicate an 8-minute error in calculations, we can only gratefully accept this divine gift. If I allowed that we could ignore these 8 minutes, I would make the necessary adjustments to my hypotheses. But since ignoring them would be unacceptable, these 8 minutes indicate the path to a complete transformation of astronomy. The discrepancy between circular and true orbits could only be revealed through precise measurements and bold acknowledgement of facts. Harmonious proportions adorn the universe, but harmony must align with experience. Kepler was shaken by the necessity to discard circular orbits and question his faith in a divine geometer. Cleansing the Augean stables of astronomy from circles and spirals, he was left, in his own words, with a cartload of manure, with a flattened circle, something like an oval. Ultimately, Kepler realized that his delight in circles had been an illusion. According to Copernicus, the Earth was a planet, and Kepler understood with complete clarity that it, ravaged by wars, plagues, famine, and other calamities, was far from perfection. Kepler, one of the first since antiquity, suggested that planets are material objects composed of the same imperfect substance as Earth. And if the planets are imperfect, why cannot their orbits be the same? He attempted to calculate various oval-shaped curves, but made some arithmetic errors, which initially led him to discard the correct answer. After several months, in despair, he tried the formula for the ellipse, first derived in Alexandria by Apollonius, and found magnificent agreement with Tycho Brahe's observations. The truth of nature, which I rejected and cast out, returned stealthily through the back door, changing its guise to be accepted. What a fool I was. Kepler discovered that Mars moves around the Sun, not in a circle, but other planets orbit the Sun in much less elongated orbits than the ellipse, and I would advise Tycho Brahe to study the motion of, say, Venus. Kepler might never have discovered the true planetary orbits. In such orbits, the Sun is not at the center, but is offset towards the foci of the ellipse. When a planet approaches the Sun, its motion accelerates, and when it moves away from the Sun, it slows down. This motion can be described as follows. Planets are constantly falling towards the sun, but never reach it. Kepler's first law of planetary motion is very simple. A planet moves in an ellipse, with the sun located at one of the foci. In uniform circular motion, an equal angle or segment of the arc is covered in equal time, so it takes twice as long to traverse 2/3 of a circle as it does to traverse 1/3. Kepler discovered that in the case of elliptical orbits, something different occurs. As planets move along their orbits, the line connecting them to the sun sweeps out small wedge-shaped areas within the ellipse. When planets are close to the sun, they cover a relatively large arc in a given time interval. However, the area corresponding to that arc is not very large because the planet is near the sun. When a planet is far from the sun, it covers a significantly smaller arc in the same amount of time. But that arc corresponds to a larger area since the sun is much farther away. Kepler found that these two areas are exactly equal to each other, regardless of how long or narrow the orbit corresponds to the planet's distant position from the sun. The area of the shorter but wider region that the planet sweeps out when close to the sun is exactly equal. This was Kepler's second law. Planets sweep out equal areas in equal times. The first two laws of Kepler may seem somewhat abstract and far removed from life. Planets move in ellipses and sweep out equal areas in equal times. Well, so what? Circular motion is easier to imagine. We could dismiss these laws as mere empty mathematical musings, detached from everyday life. But these laws govern the planets just as they govern us, glued by gravity to the surface of the Earth, hurtling through interplanetary space. We move according to the laws of nature first discovered by Kepler. When we send spacecraft to other planets, when we observe binary stars, when we track the motion of distant galaxies, we find that Kepler's laws are fulfilled throughout the universe. Many years later, Kepler formulated his third and final law of planetary motion, a law that connects the movements of different planets and reveals the workings of the clockwork of the solar system. He presented it in a book titled Harmonices Mundi. He believed many things were manifestations of a universal harmony, the order and beauty of planetary movements, the existence of mathematical laws explaining this motion, an idea stemming from Pythagoras, and even the musical harmony of the spheres. The orbits of planets, except for Mercury and Mars, differ so little from circular ones that we cannot depict these differences even on the most precise diagrams. For us, Earth is a moving platform from which we observe the movements of other planets against the backdrop of distant constellations. The inner planets move quickly along their orbits. This is why Mercury rightfully bears the name of the messenger of the gods. Venus, Earth, and Mars. Each successive planet orbits the Sun more slowly than the one before it. The outer planets, such as Jupiter and Saturn, travel with a majestic slowness, as befits the kings of the gods. Kepler's third law, or the law of harmony, states that the squares of the periods of the planets, the intervals in which they complete a full orbit, are proportional to the cubes of their average distances from the Sun. The greater the distance to a planet, the slower it moves, strictly according to the mathematical law. P squared equals A cubed, where P corresponds to the period of the planet's orbit around the Sun, measured in years, and A is the distance of the planet from the Sun, measured in astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. Jupiter, for example, is located 5 astronomical units from the Sun. Thus, the square of Jupiter's orbital period equals 125. What number, when multiplied by itself, gives 125? It seems that 11 is quite close to what we need, and indeed, the period of Jupiter's orbit around the Sun is 11 years. Similar reasoning applies to any planets, asteroids, and comets. Not satisfied with the natural laws of planetary motion, Kepler sought to find a more fundamental reason underlying them, a kind of influence of the Sun on the kinematics of the worlds. Planets accelerated their motion as they approached the Sun and slowed down as they moved away from it. Somehow, distant planets sensed the presence of the Sun. Magnetism was also an influence felt at a distance, and in an incredible foresight of the idea of universal gravitation, Kepler suggested that the fundamental reason was similar to magnetism. My aim is to show that the celestial machine should be likened not to a divine organism, but rather to a clockwork, as nearly all the numerous movements occur under the influence of one very simple magnetic force. Just as in a clock mechanism all movements are caused by a simple weight, magnetism and gravity are certainly not the same. Yet it is breathtaking to consider how fundamental Kepler's innovation was. He proposed that quantitative physical laws applicable on Earth underlie the principles governing the heavens. This was the first non-mystical explanation of motion observed in the sky. It made Earth a part of the cosmos. Astronomy, he said, is a part of physics. Kepler stands alone in history. The last scientist engaged in scientific astrology was also the first astrophysicist. Not inclined to humble prayer over his discoveries, Kepler characterized them as follows. This is a symphony of voices, allowing a person to play the music of eternity in less than an hour, and to feel, even if only slightly, the pleasure of God, the supreme artist. I freely succumb to sacred frenzy, he concluded, and I write this book so that it may be read, whether now or only by future generations. It may wait for its reader for as long as 100 years, just as the Lord himself waited 6,000 years for his witness. In the Symphony of Voices, Kepler believed that the speeds of motion of each planet correspond to certain notes of the Latin musical scale widely used in his time: do, re, mi, fa, sol, la, si, do. He claimed that our planet corresponds to fa and mi in the harmony of spheres, that Earth always reproduces these sounds, and that they are directly connected to the Latin word famus, hunger. He argued, not without success, that Earth most closely fits the description of a lonely vale of tears. Exactly 8 days after Kepler discovered his third law, an event occurred that embroiled Prague in the 30 Years' War. Military upheavals destroyed the lives of millions, and Kepler, among others, lost his wife and son in an epidemic brought by soldiers. His royal patron was overthrown, and he was excommunicated from the Lutheran Church for his uncompromising individualism in matters of faith. Kepler became a refugee once again. The conflict, which both Catholics and Protestants proclaimed a holy war, was more an exploitation of religious fanaticism by those who craved land and power. In the past, wars typically ended when warring princes exhausted their resources, but now organized looting was employed to sustain an active army. The terrified population of Europe helplessly watched as plows and sickles were literally reforged into swords and spears. Some examples can now be seen in the Graz arsenal. Waves of rumors and paranoia swept through countries, crashing down on the most vulnerable. Among many other victims were lonely old women suspected of witchcraft. Kepler's mother was taken away in the middle of the night, stuffed into a laundry chest. In Weidstadt, Kepler's hometown, between the 16th and 17th years, about 3 women were tortured and executed each year as witches, and Katharina Kepler was a cantankerous old woman. She got into disputes that irritated the local nobility and sold sleeping potions, possibly hallucinogens, like those prepared by Mexican curanderos at the time. Russian curanderos, healers in Spain and Latin America, primarily treating mental illnesses with the magic of herbs and other folk medicine, were believed to have the Quran dirus that cleanses the soul by expelling the spirits responsible for mental illness. Unfortunate Kepler believed he had contributed to her arrest in some way. The thing is, he wrote one of the first works of science fiction intended to clarify and give a potpourri of science. The book was called Somnium, the Dream. It described a journey to the moon, in which cosmic travelers from the lunar surface observe the wondrous planet Earth slowly rotating in the sky above them, changing perspective. We can imagine how measures were turned during Kepler's time. One of the main arguments against the idea of Earth's rotation was that people do not feel this rotation. Remember, Kepler tried to depict Earth's rotation in a more plausible, striking, and understandable way, as most cannot be mistaken. I prefer to be on the side of the majority, so I made great efforts to be understood by as many people as possible. At another time, he notes in a letter, "Do not condemn me to mere routine mathematical calculations. Leave me time for philosophical speculations, the only pleasure I have." Tycho Brahe, like Kepler, was far from a hostile attitude towards astrology, although he carefully distinguished his own secret version of astrology from the more common ones and variants, which he considered conduits of superstition. In his book, Astronomiae Instauratae Mechanica, published in 1598, he argued that astrology actually deserves more trust than is commonly thought, provided that the schemes of the positions of the stars are properly refined. Brahe wrote, "I have been engaged in alchemy as well as the study of celestial phenomena since I was 23 years old, but both of these pseudosciences, he believed, harbor secrets too dangerous for mere mortals, although completely safe, in his opinion, for those princes and kings who employed him." Brahe upheld a long and truly dangerous tradition among some scholars, convinced that secret knowledge could only be entrusted to them, as well as to secular and spiritual authorities. It was futile and even reckless to make such knowledge public. Kepler, on the other hand, lectured on astronomy in schools, published extensively, often at his own expense, and wrote science fiction that was certainly not intended for his scholarly colleagues. While he may not have been a popularizer of science in the modern sense, the shift in positions within just one generation that separated Brahe and Kepler speaks volumes. The invention of the telescope marked the beginning of what Kepler called lunar geography. In his dream, he depicts the moon as abundant with mountains and valleys, porous, as if riddled with certain caves. This was a response to Galileo's discovery, who had recently seen lunar craters through the first astronomical telescope. Kepler imagined the moon inhabited by beings well adapted to the harsh environment. He depicted the slowly rotating Earth as seen from the lunar surface, and speculated that the continents and oceans of our planet evoke associations similar to the human face that we see on the moon. The convergence of the shores of southern Spain and northern Africa in the Strait of Gibraltar conjured in his mind the image of a virgin in flowing robes, about to kiss her beloved. Although, in my opinion, it resembles touching noses more. And remembering the long lunar days and nights, Kepler wrote about a very harsh climate on the moon and the destructive fluctuations from heat to cold, which is entirely accurate. Of course, he was right. He believed that the moon has a full atmosphere, oceans, and inhabitants. His hypothesis about the origin of lunar craters is the most curious. He claimed that they give the moon a resemblance to a boyish face pockmarked with smallpox. He did not err in asserting that craters are depressions rather than elevations. In his own observations, he noted the ridges around many craters and the existence of central peaks within the craters. However, he thought that the proper circular shape of the craters implied such a level of order that only the presence of intelligent life could explain it. He did not suspect that the fall of enormous stones from the sky would cause explosions perfectly symmetrical in all directions, leaving behind round pits. This is the origin of most craters on the moon and on other terrestrial-type planets. Instead, Kepler concluded the existence of some intelligent race capable of creating such depressions on the surface. This race would need to be numerous enough for one group to use the newly created depression, while another constructed the next one. Kepler countered the argument about the improbability of such grand construction endeavors by referring to the Egyptian pyramids and the Great Wall of China, which, as it turned out, are indeed visible from low Earth orbit. This is a widespread myth. In reality, neither the pyramids nor the Great Wall of China are visible to the naked eye from orbit. The idea that geometric order reveals a hidden intelligence behind it was central to Kepler's life. His arguments regarding lunar craters foreshadow the future debate about the nature of Martian canals. Listen to Chapter 5. It is astonishing that the search for extraterrestrial life was initiated by the same generation that invented the telescope, and it was undertaken by the greatest theorist of his time. Specific places in the dream are clearly autobiographical. The main character, for example, pays a visit to Tycho Brahe. His parents trade in medicines. His mother befriends spirits and demons, one of whom eventually agrees to arrange a journey to the moon. For us, it is clear that in a dream, a person must sometimes experience such freedom of imagination that is utterly impossible in the world of sensory perception. But this thought did not resonate with many of Kepler's contemporaries, and science fiction was a novelty during the 30 Years' War. Kepler's book was used as evidence that his mother was a witch. Forgetting other sorrows, Kepler rushed to Württemberg, where he found his 74-year-old mother shackled and imprisoned in a Protestant jail, where, like Galileo in a Catholic one, she was threatened with torture. As a scholar should, he began by searching for natural causes of various events that led to accusations of witchcraft, including minor ailments that the residents of Württemberg attributed to her spells. His investigation ended in success, a triumphant victory of reason. The nation believed, which was essentially the entirety of Kepler's life. His mother was expelled from Württemberg, threatened with death if she ever dared to return. It was Kepler's bold intervention that apparently led to the issuance of a ducal decree prohibiting prosecution for witchcraft in the presence of such weak evidence. The vicissitudes of war deprived Kepler of his livelihood, and he struggled to survive, begging for money and patronage. He cast horoscopes for Duke Wallenstein, just as he had done for Rudolf II, and spent his last years in the town of Telts, now Rogan, Poland, under Wallenstein's control. The epitaph he composed for himself read, "I measured the heavens, now I measure shadows. To the sky was bound the mind, to the earth the remains. In the original, rationem ad coelum, ad terram reliquiae." But the 30 Years' War left no trace of his grave. If a memorial plaque were established today, paying tribute to the courage of the scholar, it should read, "He preferred harsh truth to his dearest illusions." Johann Kepler believed that a day would come when researchers, unafraid of the vast expanses of space, would venture into the sky on ships with sails adapted to the celestial winds. And today, these researchers are automaton-like humans. In their journeys through the boundless cosmic spaces, they rely on the infallible guidance of the 3 laws of planetary motion that Kepler derived during a life filled with arduous labor and remarkable discoveries. The lifelong quest of Johann Kepler to understand the motion of planets and to uncover harmony in the heavens was resolved 36 years after his death in the works of Isaac Newton. Newton entered this world on Christmas Day in 1642, so tiny that, as his mother told him many years later, he could have fit into a liter beer mug. Sickly, deprived of parental love, irritable and unsociable, Isaac Newton was likely the greatest scientific genius to ever live. Even in his early youth, Newton was troubled by useless questions, such as whether light is a substance or an accident, or how gravity can exert influence through empty space. Accident, from the Latin accidens, refers to a chance occurrence, a temporary, transient, non-essential property of a thing, as opposed to an essential one. In this case, the question should be understood as whether light is a form of matter, substance, or particles, or merely a property, a state, an external manifestation of matter. Later, Newton leaned towards a substantial view of light, the corpuscular model, and debated with giants, insisting on the wave nature of light. This dispute was only resolved in the 20th century when the theory of relativity and quantum mechanics allowed for the construction of a theoretical model of light that described both its corpuscular and wave properties, manifesting depending on the conditions of observation. This understanding of the nature of light is known as wave-particle duality. He early concluded that the traditional Christian doctrine of the Holy Trinity was a misinterpretation of Scripture. His biographer, John Maynard Keynes, asserts that in his beliefs he was closer to Buddhism than to Judaism. Maimonides, a Jewish philosopher who lived in the 11th and 12th centuries, a systematizer of the laws of the Torah, was a rationalist who sought to purify faith from the element of miracle, thereby incurring the hostility of adherents to religious tradition. He reached this conclusion not through so-called rational or skeptical arguments, but solely through the interpretation of ancient authorities. He was convinced that the text of Revelations provided no ground for the doctrine of the Trinity, which, in his view, arose from later forgeries. The God of Revelations was the only God, but this remained a terrible secret that Newton was forced to conceal throughout his life with immense effort. Like Kepler, he was not free from the superstitions of his time and frequently turned to mysticism. Indeed, most of Newton's intellectual achievements can be linked to his oscillations between rationalism and mysticism. In 1663, at the age of 20, He bought a book on astrology at a fair in Stourbridge out of curiosity to see what it was about. He flipped through it until he reached an illustration he could not understand because he was unfamiliar with trigonometry. He purchased a book on trigonometry, but soon discovered he could not grasp the geometric reasoning. Then he found Euclid's Elements of Geometry and began to read. 2 years later, he invented differential calculus. Newton's student years were enchanted by the mystery of sunlight. He developed a dangerous habit of looking at the reflection of the sun in a mirror. After a few hours, I brought my eyes to such a state that even without looking at bright objects, I saw the sun before me. I could neither write nor read. And to restore my sight, I locked myself in a dark room for 3 days and tried, with all my might, to distract my imagination from the sun. For as soon as I thought of it, I immediately saw its image, even though I was in darkness. In 1666, at the age of 23, when Newton was studying at the University of Cambridge, an epidemic of plague forced him to spend a year in seclusion in the village of Woolsthorpe, where he was born. During this time, he occupied his leisure by developing differential and integral calculus, probing the foundations of the nature of light, and laying the groundwork for the theory of universal gravitation. In the history of physics, there was only one such year, 1905, the miraculous year of Einstein. When Newton was asked how he managed to make his outstanding discoveries, he struggled to respond. "I thought about them." His work was so significant that his teacher at Cambridge, Isaac Barrow, yielded his chair of mathematics to him. When the young man returned to college 5 years later, he was described as follows at over 40. His servant says, "I have never seen him rest or entertain himself, ride, walk, play ball, or engage in other similar exercises. He considered any hour not spent on research a wasted hour, to which he was so attached that he rarely left his study except during lecture hours, which only a few came to hear, and even fewer understood. Thus, often, in the absence of listeners, he, as they say, lectured to the walls." Newton's students, like Kepler's listeners, never knew what they missed. Newton discovered the law of inertia, according to which a moving object tends to continue moving in a straight line until some external force diverts it from that path. The moon, according to Newton, would fly off in a straight line, tangent to its orbit, if not for a special force pulling it towards the Earth, causing it to constantly deviate from its straight path into a circular one. Newton called this force gravity and believed it acted at a distance between the Earth and the moon. Not from visible connection, yet the Earth constantly attracts the moon to itself. Using Kepler's third laws, Newton mathematically revealed the nature of gravitational force. Unfortunately, in his outstanding work, Principia, Newton did not give due credit to Kepler. However, in 1686, in a letter to Duval, he mentioned his law of gravitation. "I confirm that I derived it from Kepler's theorem about 20 years ago." He demonstrated that the same force that causes an apple to fall to the Earth keeps the moon in orbit around the Earth and accounts for the orbits of Jupiter's moons, which had only recently been discovered. Throughout history, things have a tendency to fall down. Humanity has been confident in the moon's orbit around the Earth throughout its history. Newton was the first to understand that one and the same force is responsible for both phenomena. This is why the gravity discovered by Newton is called universal. The same law of gravitation applies throughout the universe. This law obeys the inverse square rule. The force decreases inversely proportional to the square of the distance. If the distance between two objects doubles, the gravitational force between them decreases by a factor of 4. With a tenfold increase in distance, gravity becomes 10 squared, that is, 100 times weaker. It is evident that the force must be inversely related to the distance, that is, decrease as distance increases. If forces increased with distance, the greatest force would act between the most distant objects, and then, I believe, all the matter in the universe would be drawn into one gigantic cosmic heap. Nothing of the sort happens, so gravity must decrease with distance. This is why the motion of planets and comets slows down far from the sun and accelerates near it. The attraction acting on them is weaker the farther they are from the sun. From Newton's principles, all three of Kepler's laws can be derived. Kepler's laws were empirical, based on the meticulous observations of Tycho Brahe. Newton's laws are theoretical, rather simple mathematical abstractions from which all of Brahe's measurements can ultimately be derived. This allowed Newton, without concealing his pride, to write in his Principia, "Now I shall demonstrate the foundation of the system of the world." Subsequently, Newton presided over the Royal Society, served as warden, and later as director of the Mint, where he devoted all his energy to combating counterfeiters. His natural gloominess and reclusiveness grew. He decided to cease his scientific pursuits, which had embroiled him in fierce disputes with other scholars, primarily over the priority of discoveries. Some even spread rumors that he had suffered something akin to a nervous breakdown. Nevertheless, until the very end of his life, Newton continued experiments on the border of chemistry and alchemy, and recent research suggests that his ailment was not so much of a psychological nature as related to poisoning by heavy metals, caused by the systematic ingestion of small amounts of arsenic and mercury. For chemists of that time, taste testing was a fairly common method of analysis. Despite this, Newton's remarkable intellect remained intact. In 1696, Swiss mathematician Johann Bernoulli approached his colleagues with a proposal to solve an unresolved problem about the brachistochrone. To find the curve connecting 2 points along which a body moving under the influence of gravity will travel from one point to another in the least time. Initially, Bernoulli set a 6-month deadline, but later extended it to 1.5 years at the request of Leibniz and one of the leading scientists of the time, independently of Newton, who had ventured into differential and integral calculus. The task reached Newton at 4 o'clock in the afternoon on January 29th, 1697. The next morning, before leaving for work, he brought to life a new branch of mathematics called variational calculus, applied it to the brachistochrone problem, and sent his solution, which at his request was published anonymously. However, the brilliance and originality of the work revealed its author. When Bernoulli saw the solution, he remarked, "We recognize the lion by his tracks." Newton was 55 at that time. At the twilight of his life, his main intellectual efforts were directed at calibrating and reconciling the chronology of ancient cultures in the traditions of past historians such as Strabo and Eratosthenes. In his last work, The Chronology of Ancient Kingdoms Amended, published posthumously, Newton provided numerous astronomical reference points for various historical events. reconstructed the architecture of Solomon's temple, provocatively claimed that all the constellations of the northern hemisphere were named after characters, attributes, and events from the Greek myth of Jason and the Argonauts, and finally, on this basis, suggested that the gods of all civilizations, with the exception of his own, were actually ancient kings and heroes who were deified by subsequent generations. Kepler and Newton embody a turning point in human history, the discovery that all nature is governed by extremely simple mathematical laws, that the same laws apply on Earth and in the heavens, and that there is a correspondence between the way we think and the principles governing the world. They held immense respect for the accuracy of empirical data, and their highly precise predictions of planetary motion became irrefutable evidence that humanity is capable of comprehending the cosmos to its very depths. Our modern global civilization, our worldview, and our contemporary explorations of the universe owe much to their enlightenment. Newton always asserted the priority of his discoveries and fiercely competed with his fellow scholars. It cost him nothing to postpone the publication of his law of inverse squares for a decade or two. But in the face of the grandeur and mystery of nature, he, like Ptolemy and Copernicus, was joyfully excited and disarmingly humble. Just before his death, he wrote, "I do not know what I appear to the world, but to myself I seem to have been only a boy playing on the seashore, diverting myself, finding either an especially smooth pebble or an unusually beautiful shell, while the vast ocean of truth lies before him completely unexplored." Although this phrase is attributed to Newton, it was never published under his name. It first appeared in print in 1820 in a collection of quotes referencing Andrew Michael Ramsay. In 1855, Newton's biographer, David Brewster, quoted these words as having been spoken by Newton shortly before his death. However, in the year of Newton's death, Ramsay was in France, and it is highly likely that this phrase is a legend, similar to the story of the apple that inspired Newton to discover the law of universal gravitation. Earth is a wonderful and relatively calm place. The course of events changes, but slowly. One can live an entire life and never encounter a natural disaster more terrifying than a hurricane. This makes us complacent, relaxed, and carefree. But natural history inexorably testifies that measures have been subject to devastation. Even we, humans, have achieved dubious technical successes in orchestrating our own catastrophes, both intentionally and through negligence. The landscapes of other planets, where remnants of a distant past remain, reveal countless traces of monumental cataclysms. It all comes down to the timescale. Events unimaginable over a span of 100 years may become inevitable over 100 million years. Yet even on Earth, even in our century, very strange natural phenomena have occurred. Early in the morning, on the 30th of June, in 1908, a gigantic fireball streaked across the sky at tremendous speed in central Siberia. Where it touched the horizon, an explosion of incredible force occurred over an area of 2,000 square kilometers, toppling forests, and near the impact site, a fireball ignited thousands of trees. The explosion generated a shock wave in the atmosphere that circled the Earth twice. For the next 2 days, so much fine dust remained in the air that the light scattered by it allowed people to read newspapers in the streets of nighttime London from 10,000 kilometers away. The government of Tsarist Russia did not concern itself with investigating such a mundane event, which moreover occurred in distant Siberia among the dark Tungus people. Only 10 years after the revolution was a research party sent to analyze the soil and interview witnesses. Here are some of the accounts they collected. Early in the morning, while everyone was still asleep, a strong jolt threw a suitcase into the air along with everyone inside. When they fell to the ground, the whole family was covered in bruises, and Akulina and Ivan even lost consciousness. When they came to, they heard a terrible noise and saw that the forest around them was burning, and much of it had been flattened. At breakfast, I was sitting on the porch of the house at the factory in Navarra, facing north. Just as I swung my axe to fit a hoop onto a spool, the sky suddenly parted, and fire appeared wide and high above the forest. The entire northern part of the sky was ablaze. At that moment, I felt so hot as if my shirt had caught fire. I wanted to tear off and throw away my shirt. But at that moment, the sky closed, and there was a loud bang that threw me to the ground 3 fathoms away. For a moment, I lost consciousness, but my wife, who ran out of the hut, brought me back to my senses. After the bang, there was such a noise, as if stones were falling or cannons were firing, and while I lay on the ground, I pressed my head down, fearing that my skull would be crushed. At the moment when the sky opened in the north, a hot wind rushed past, like from a cannon, leaving trails on the ground. When I sat down to breakfast near my plow, suddenly there were sounds like cannon shots. The horse fell to its knees from the north, and flames shot up over the forest. Then I saw the spruce forest bend down. I thought a hurricane had grabbed the plow with both hands to prevent it from being swept away. The wind was so strong that it blew some soil off the surface of the ground. And then this hurricane, in the barn, drove the water in a torrent. I could see everything clearly because the tower was on a hill. The noise frightened the horses so much that they bolted in panic, pulling the plows in different directions. The carpenters, working on the construction of the barn, after the first and second bangs, crossed themselves in complete bewilderment, and when the third bang sounded, the carpenters were thrown back like splinters. Some were so stunned and terrified that we had to bring them to their senses and calm them down. We all also abandoned our work and went to the village. There, crowds of locals gathered in the street, passionately discussing and interpreting this extraordinary phenomenon in every possible way. I was in the field, just having harnessed the horse to the harrow, and was about to tie another one, when I suddenly heard what sounded like a faint gunshot to my right. I immediately turned and saw a flaming object flying, elongated in shape, wider at the tail, colored like fire in the daytime, much whiter than the sun, but much weaker in brightness, so that one could look at it. Behind the flame, there was what looked like dust, swirling in curls, and from the flame, there were still blue streaks. As soon as the flame disappeared, sounds louder than gunshots were heard. The ground trembled, and the glasses in the windows of the winter hut rattled. I was washing wool on the riverbank when suddenly I first heard a noise like the wings of a frightened bird, and a wave went upstream along the river, like ripples, after which there was one sharp bang. The bang was so strong that one of the workers fell into the water. This remarkable event is known as the Tunguska meteorite fall. Some scientists have speculated that it was caused by a piece of antimatter that annihilated upon contact with ordinary matter on Earth, producing a gamma-ray burst. However, The absence of radiation contamination at the impact site does not support this hypothesis. Others claimed that a small black hole penetrated the Earth's crust in Siberia and emerged on the other side of the planet. But records of atmospheric shock waves do not indicate any object that flew out of the North Atlantic later that same day. Perhaps it was a spacecraft from some unimaginably advanced extraterrestrial civilization that crashed in a remote area of an unknown planet due to insurmountable technical problems. But no traces of such a craft have been found at the impact site. Each of these hypotheses has been proposed before, some more or less seriously. None of them has compelling evidence. The main feature of the Tunguska phenomenon is that both the terrible explosion and the powerful shock wave and the gigantic forest fire were present, yet no impact crater was formed at the site. It seems there is only one explanation that does not contradict the facts. In 1908, a fragment of a comet fell to Earth. Countless objects, rocky, metallic, icy, are scattered across the boundless interplanetary expanses. Some partially consist of organic molecules. There are those the size of a speck of dust, but there are also irregularly shaped fragments the size of Nicaragua or Bhutan. Occasionally, a planet happens to be in their path. The Tunguska meteorite was likely produced by an icy fragment of a comet that measured about 100 meters in diameter, roughly the size of a football field, weighed 1 million tons, and traveled at a speed of about 30 kilometers per second. If such a collision were to occur today, it could mistakenly be perceived as a nuclear explosion, especially in a moment of panic. The fall of comets can produce all the effects characteristic of a megaton nuclear explosion, including a mushroom cloud, with two exceptions. There would be no gamma radiation and no radioactive fallout. Could a rare but natural event, like the fall of a large comet fragment, lead to the outbreak of nuclear war? It would be a strange scenario. A large comet falls to Earth, as has happened before with millions of other comets, and our civilization immediately self-destructs. It would do us well to learn more about comets, collisions, and catastrophes. For example, on the 22nd of September in 1979, an American satellite registered a bright double flash of light somewhere on the border of the South Atlantic and the western part of the Indian Ocean. Satellites had been monitoring compliance with the treaty banning the testing of nuclear weapons in the atmosphere, outer space, and underwater since 1963. The first assumption was that these were secret tests of low-yield nuclear devices, 2 kilotons, created by South Africa or Israel, approximately 6 times smaller than the bomb dropped on Hiroshima. The political consequences were very serious and were studied worldwide. But what if these flashes were caused by the fall of a small asteroid or comet? This explanation was deemed the most likely when aerial reconnaissance found no traces of radioactivity in the area of the flashes. Here is an example of how dangerous it is in our nuclear age not to pay due attention to impacts from space. Comets are mostly made of ice, frozen water, H2O, with small amounts of methane, CH4, and ammonia, NH3. When a modestly sized comet fragment enters Earth's atmosphere, it produces a huge shining fireball capable of igniting trees, and a powerful shock wave that can topple forests and is registered worldwide. However, it is not necessary for a large crater to form on the surface. Upon entering Earth's atmosphere, comets can melt, and in such cases, only a small number of fragments of the comet are found, likely only rare grains and not the icy components of the comet's nucleus. Soviet scientists and Emlyn Sabatovich discovered a large number of microscopic diamonds scattered at the site of the Tunguska meteorite fall. Such diamonds had been found before in fallen meteorites, the origin of which could be linked to comets. If on a clear night, as darkness falls, one carefully observes the sky without distraction, one can sometimes catch a glimpse of a brief flash of a meteor directly overhead. On certain nights, always falling on the same calendar dates, there is a chance to admire a meteor shower, a kind of natural fireworks display, a celestial show. The peaks of activity for the most intense meteor showers are the 3rd of January, Quadrantids, the 12th of August, Perseids, and the 14th of December, Geminids. These meteors are smaller than a mustard seed, more like settling dust than falling stars. As they enter the Earth's atmosphere, meteor particles heat up due to friction, briefly flash brightly, and perish at an altitude of about 100 kilometers. Meteors are remnants of disintegrated comets. The idea of a connection between meteors, meteorites, and comets was first proposed by Alexander Bulygin in his comprehensive popular science work, Cosmos, published from 1845 to 1862. It was reading Humboldt's early works that prompted Charles Darwin to attempt to combine geographical studies with natural history. Shortly thereafter, he agreed to take a position as a naturalist aboard the ship Beagle, which ultimately led to the publication of On the Origin of Species. Old comets, repeatedly passing near the sun and heating up, undergo disintegration, evaporation, and cease to exist. Their remnants are scattered along the entire cometary orbit. Where this orbit intersects with Earth's, we are met by a meteor shower. Some part of the shower always coincides with the same section of Earth's orbit, and therefore the meteor shower is observed every year on the same day. The 30th of June in 1908 was the day of the meteor shower of Beta Taurids associated with Comet Penke. It is possible that the primary cause of the Tunguska phenomenon was a fragment of this very comet, a piece significantly larger than the tiny grains that cause harmless meteor flashes. Comets have always been sources of fear and superstitious awe. Their unexpected appearance challenged the notion of an unchanging and divinely ordered cosmos. It seemed incredible that the eye-catching streak of milky white flame, which rises and sets with the stars each night, appeared without any reason and is not some sort of omen. Thus arose the idea that comets are harbingers of catastrophe, signs of divine wrath, predicting the death of rulers and the fall of kingdoms. In Babylon, comets were not considered heavenly beards. The Greeks spoke of flowing hair, and the Arabs referred to them as flaming swords. In the time of Ptolemy, comets were meticulously classified by shape: rays, tubes, jugs, and so on. Ptolemy believed that comets bring wars, hot weather, and upheaval. Some medieval depictions of comets resemble unidentified flying crucifixes. Andreas G., a figure from the Lutheran Church, the Bishop of Magdeburg, published a theological memorandum in 1578 about a new comet, in which he suggested that the thick smoke of human sins, foul and repugnant before the face of the Lord, rises every day, every hour, every moment, gradually becoming so dense that it forms comets with curling and intertwining hair that eventually ignite from the wrath of the supreme heavenly judge. To this, he was countered that if comets were smoke from sins, they would be constantly burning in the heavens. The oldest record of the appearance of Halley's Comet, the oldest record of comets, was found in a Chinese book by Prince Huoyan, who did not accompany the ruler on a military campaign. This was in 1057 BC. The proximity of Halley's Comet to Earth in 66 AD likely explains the mention of the siphon of the sword, which hung over Jerusalem for an entire year. The Jewish historian Josephus Flavius later linked this phenomenon to the fire in the Temple of Jerusalem in 70 AD. And the signs of the Lord were clear, and a comet shone in the sky over the city for an entire year, and this light was like a punishing sword. In 66 AD, the Normans witnessed another return of Halley's Comet, as it became a portent of the fall of a certain kingdom. The comet, in some sense, pointed to the imminent invasion of England by William the Conqueror. The appearance of the comet reflects a peculiar chronicle of that time. The tapestry from the battle in 1301. Giotto, one of the founders of modern realistic painting, documented another appearance of Halley's Comet, captured in the scene of the Nativity of Christ. The Great Comet of 1466 caused panic in Christian Europe. Christians believed that the Lord, sending comets, might be on the side of the Turks, who had recently captured Constantinople. Leading astronomers of the 16th to 18th centuries were fascinated by comets, and even Newton was not indifferent to them. Kepler wrote that comets race through space like fish in the sea, but gradually dissipate in sunlight, as comet tails are always directed away from the sun. David Hume, in many ways an uncompromising rationalist, jokingly speculated that comets might be reproductive cells, eggs, or sperm of planetary systems, and that planets engage in a sort of interstellar copulation. Newton, even in his student days before the invention of the reflecting telescope, spent many sleepless nights trying to find comets in the sky with the naked eye, and he worked so hard that he even fell ill from exhaustion. Following Tycho Brahe and Kepler, Newton concluded that comets do not move within the atmosphere of our planet, as Aristotle and many other scholars believed, but are much farther away than the Moon, although closer than Saturn. Like planets, comets reflect sunlight, and therefore those who assign comets to the realm of fixed stars are completely mistaken, for in that case they would not be illuminated by our sun any more than the planets in our regions are illuminated by fixed stars. Newton showed that comets, like planets, move in ellipses. Comets constitute a type of planet that orbits the sun in highly eccentric ellipses. This demystification, expressed in the prediction of the regularity of cometary orbits, led Newton's friend Galileo to calculate in 1707 that the comets of 1503, 1607, and 1608 were manifestations of the same comet with a 76-year interval. Galileo predicted its return in 1758. Precisely at the appointed time, the comet appeared in the sky and was named after the scientist posthumously. In human history, Halley's Comet has played an interesting role, and it may become the first celestial guest to which a space probe will be launched during its next visit in 1986. The first encounter of a spacecraft with a comet occurred on the 11th of September in 1985, when the OSIRIS probe, launched in 1978 to study solar wind, was redirected and passed through the tail of Comet Gabriella 7,800 kilometers from its nucleus. The probe was not equipped with cameras. In 1986, Halley's Comet was studied by an entire armada of 5 spacecraft. 2 Soviet interplanetary stations, Vigodan and Vega 2. After landing their descent vehicles on Venus, they approached the nucleus of the comet to within 89,000 kilometers. The Giotto spacecraft, launched by the European Space Agency, passed just 600 kilometers from the nucleus. 2 Japanese probes studied the comet from a greater distance. SUFI, maximum approach of 150,000 kilometers, and Sake, 7 million kilometers. Modern planetologists sometimes assert that collisions with comets could have significantly contributed to the formation of planetary atmospheres. For example, all the water currently found in Mars's atmosphere could have originated from the fall of a small comet. Recent studies of Mars show that about 3 billion years ago, there were oceans of liquid water on its surface. There is still significantly more water in the soil and polar caps of Mars than in its atmosphere. Newton wrote that the substance comprising the tails of comets disperses in interplanetary space and is gradually attracted by nearby planets. He was convinced that Earth is gradually losing water, absorbed by plants and decay, turning into dry land. The amount of liquid, if it were not replenished from outside, would continuously decrease and eventually disappear. It seems that Newton believed that Earth's oceans have a cometary origin, and that life is possible only because cometary material falls onto the planet. In his mystical reflections, he goes even further. Moreover, I suspect that the gas that constitutes the lesser but finest and best part of our air, which is required for sustaining life for all living beings, also primarily originates from comets. As early as 1868, astronomer William Higgins discovered that certain details in the spectrum of comets and natural gas coincided. William Higgins, 1824, 1910, was an English astronomer who was one of the first to apply spectral analysis and photography in astronomy. In 1864, he definitively established the existence of gaseous nebulae and studied the chemical composition of stars. In 1868, he determined the radial velocities of several bright stars by the shift of lines in their spectra, and showed that the spectrum of comets differs from those of gaseous nebulae, noting that carbon bands exist in the spectrum of comets, and he was one of the first to observe solar prominences outside of eclipses. In 1882, he obtained a photograph of the unshielded solar corona. In 1902, he studied the spectrum of radiation. Thus, Higgins discovered organic matter in the composition of comets. In subsequent years, cyanogroup CN was identified in comet tails, consisting of carbon and nitrogen atoms, a molecular fragment that serves as the basis for cyanides. When in 1910, Earth was to pass through the tail of Halley's Comet, many people panicked, forgetting that the comet's tail is incredibly rarefied. The danger of poisoning was many times less than that posed by industrial emissions in large cities, even in 1910. Explanations did little to calm anyone. Here are some headlines from San Francisco. Screen, May 15, 1910. Comet gas chamber the size of a house. The husband is corrected due to the arrival of the comet. New York is acting strangely because of the comet. The Los Angeles A exam took a humorous tone. Hey comet, are you still not on cyanide? All humanity is waiting for a free gas chamber in anticipation of noisy fun. Many smell cyanide. A victim climbed a tree, trying to call the comet. In 1910, people hurried to throw a party, to indulge one last time before cyanide poisoning brought about the end of the world. An enterprising businessman sold anti-comet pills and gas masks. The latter turned out to be grim harbingers of the battles of World War I. Misunderstandings related to comets still occur today. In 1957, I was a graduate student at the York Observatory at the University of Chicago. One night, while on solitary duty, I heard an insistent phone call. A voice, indicating a considerable degree of inebriation, spoke into the receiver. "Let me talk to the astronomer." "How can I help?" "Well, you know, we have a party in the garden, and there's something hanging in the sky. And it's funny, if you look directly at it, it disappears. But if you don't look, it reappears." The most sensitive part of the retina is located away from the center of the field of vision. A dim star or other object can be noticed by slightly averting one's gaze. I knew that at that time there was a barely discernible comet, Arena Rala, in the sky, which had recently been discovered. So I informed him that it was probably a comet. There was a long pause, then the question, "Still a comet?" "A comet," I replied. "It's a snowball about a mile wide." And another pause hung, even longer, and on the other end they demanded, "Let me talk to a real astronomer." It is interesting to consider what phantoms political leaders will fear when Halley's Comet reappears in 1986. What other nonsense will spill out upon us? The next visit of Halley's Comet passed without any significant outburst of superstition. Probably, the research programs using spacecraft played a significant role. Additionally, this time, the famous comet did not appear particularly impressive. The last decade of the 20th century gifted us with two more bright comets, Hale-Bopp and Hyakutake, whose appearances were widely covered by the press, but almost exclusively as astronomical phenomena. Nevertheless, a new phobia did arise in the world, but this time it was linked to a very real, albeit unlikely, threat of an asteroid or comet falling to Earth. Astronomers have already established a tracking system for potentially hazardous objects. However, among them, there is not yet a single one that poses a real threat to humanity. Although planets move around the Sun in elliptical orbits, these orbits are not very elongated. At first glance, they are indistinguishable from circles. In contrast, comets, especially long-period ones, have distinctly elongated elliptical orbits. Compared to the ancient planets of the inner solar system, comets are newcomers here. Why are the orbits of planets almost circular and significantly spaced apart? If their orbits were highly elongated, the paths of the planets would intersect, and sooner or later, a collision would occur. In the early history of the solar system, there were likely many planets arriving at the stage of formation. Those that moved in intersecting elliptical orbits had a predisposition to collisions and self-destruction. Those whose orbits approached circularity had a better chance of growing and surviving. The orbits of modern planets are the paths of those that survived collisions, the natural selection of a calm and mature solar system that triumphed during an era of catastrophic impacts. At the far edges of the solar system, in darkness, far beyond the planetary orbits, lies a vast spherical cloud of trillions of cometary nuclei, which orbit the Sun no faster than participants in the Indianapolis 500 car race. Earth is located at a distance r of 1 astronomical unit, 150 million kilometers from the Sun. The length of its nearly circular orbit is approximately 2 pi r, or about 10 to the 9th power kilometers. Each year, our planet travels this distance, completing one orbit. 1 year equals 3 times 10 to the 7th power seconds. Thus, Earth's orbital speed is approximately 30 kilometers per second. Now consider the spherical cloud of comets, which, according to many astronomers, orbits the Sun at a distance of about 100,000 astronomical units. This is nearly halfway to the nearest star. From Kepler's third law, it follows that the orbital period of any such comet around the Sun is about 30 million years. For the outer regions of the solar system, one orbit around the Sun is a considerable amount of time. The length of a comet's orbit is approximately 10 to the 14th power kilometers, and its speed does not exceed 360 kilometers per hour. Typical comets look like giant swirling snowflakes in space, about 1 kilometer in diameter. Most of them never cross the conditional boundary drawn along Pluto's orbit, but sometimes a passing star creates gravitational disturbances in the cometary cloud, and some comets end up on very elongated elliptical orbits leading toward the Sun. After approaching Jupiter or Saturn, the path of such a comet may change again under their gravitational influence, and it will return to the inner solar system approximately once every century. Somewhere between the orbits of Jupiter and Mars, the comet heats up and begins to evaporate. The material streaming from the solar atmosphere, the solar wind, carries particles of dust and ice away from the comet, beginning to form its tail. If Jupiter were 1 meter in diameter, our comet would be smaller than a speck of dust. However, the tail, when fully extended, is comparable in size to the distance between planets. Appearing in the Earth's sky, a comet always sows superstitious dread in the hearts of Earthlings. But eventually, the inhabitants of Earth manage to understand that this celestial body exists far beyond the atmosphere among the planets. They calculated its orbit, and perhaps the day is not far off when a small spacecraft will be launched to study the visitor that has come to us from the realm of stars. Sooner or later, comets collide with planets. Earth and its satellite, the Moon, must undergo bombardment by comets, small asteroids, debris left over from the formation of the solar system. Since there are more small objects, the probability of a collision with them is higher. The fall of a small fragment of a comet, similar to the Tunguska meteorite, should occur roughly once every 1,000 years, while a collision with a large object like Halley's Comet, whose nucleus likely reaches a diameter of about 20 kilometers, could happen approximately once every billion years. According to data from the Vega and Giotto spacecraft, the nucleus of Halley's Comet has an elongated shape and measures 16 by 8 kilometers. When a small, icy fragment collides with a planet or satellite, it does not leave large scars on the surface. But if the falling object is relatively large or primarily composed of ice, a collision will cause an explosion, after which a hemispherical depression, known as an impact crater, will form on the surface. In the absence of processes that erase or bury such craters, they can be preserved for billions of years. The Moon has virtually no erosion, and therefore we see that it has far more impact craters than one would expect. Judging by the few remnants of comets, the populated regions filling our inner solar system, the lunar surface eloquently testifies to an era of world destruction that ended billions of years ago. Impact craters are found not only on the Moon. Within the inner part of the solar system, they can be discovered everywhere, from Mercury, the planet closest to the Sun, to cloud-covered Venus and Mars with its tiny moons, Phobos and Deimos. This is the so-called family of terrestrial planets, more or less similar to Earth. They have solid surfaces made of iron and stone. Their interiors vary, and the density of their atmospheres ranges from nearly complete vacuum to pressures 90 times greater than that of Earth. They crowd around the Sun, the source of light and heat, like travelers awkwardly gathered around a campfire. All the planets are approximately 4,600,000,000 years old. Like the Moon, they all bear traces of an era of catastrophic collisions that occurred in the early history of the solar system. Beyond the orbit of Mars, we enter a completely different realm, the realm of gas giants, or, as they are also called, the Jupiter group of planets. These are enormous worlds, primarily composed of hydrogen and helium, with small amounts of hydrogen-rich gases, such as methane and ammonia, and water vapor. We do not see a solid surface on them, only atmosphere and colorful clouds. These are serious planets, not mere orbs like Earth. Jupiter could contain thousands of planets the size of ours. If a comet or asteroid were to fall into Jupiter's atmosphere, we would not notice the formation of a crater, only a brief disruption in the clouds. In July 1994, the Shoemaker-Levy 9 comet crashed into Jupiter's atmosphere at a speed of about 60 kilometers per second. Even before the collision, the comet's nucleus broke apart into 24 large fragments measuring from 1 to 10 kilometers. Unfortunately, the comet's debris entered the atmosphere on the planet's unseen side, but after 40 to 50 minutes, due to Jupiter's daily rotation, the impact sites became observable from Earth. The explosion traces appeared as enormous dark spots and radiating atmospheric shock waves on Jupiter, comparable in diameter to Earth, and were observed in many observatories around the world. Nevertheless, we know that in its outer regions of the solar system, collisions have been occurring for many billions of years, as Jupiter has more than a dozen moons, 5 of which have been studied up close by the Voyager spacecraft. Here, we again find evidence of cataclysms. When the entire solar system is studied, we will likely find traces of catastrophic collisions on all worlds, from Mercury to Pluto, as well as on all moons, comets, and asteroids. In the year 2000, the Near-Shoemaker spacecraft became the first to enter orbit around the asteroid Eros. For a year, it conducted detailed studies and photography of the asteroid, and in February 2001, it made a controlled landing on it, although it was not designed for that purpose. Preliminary analysis of the obtained images indicates that most of the rocky debris found on the asteroid was ejected from one area of the surface as a result of a collision with another celestial object. On the side of the Moon facing us, about 10,000 craters can be seen through a telescope from Earth. Most of them are located on ancient lunar highlands, meaning they formed when the period of accretion of interplanetary debris was coming to an end. In the lunar seas, lowlands that were likely flooded with lava shortly after the Moon's formation, there are about 1,000 craters with a diameter greater than 1 kilometer. Thus, by very rough estimates, craters should currently be forming on the Moon at a rate of 10 to the 4th power of craters per 10 to the 9th power of years, which translates to 10 to the fifth power of years for one crater, 100,000 years. Several billion years ago, there may have been more interplanetary debris than there is now, so we will likely have to wait even longer than 100,000 years to see a new crater form on the Moon. Since the surface area of Earth is greater than that of the Moon, it should be assumed that collisions producing craters about 1 kilometer in diameter on our planet occur at intervals of about 10,000 years. The age of the meteorite crater in Arizona, which is approximately 1 kilometer in diameter, is about 20 to 30,000 years, which aligns with our very rough calculations. The fall of a small comet or asteroid on the Moon can produce an instantaneous flash bright enough to be seen from Earth. It is easy to imagine how one night, 100,000 years ago, our ancestors, idly yawning, suddenly noticed a strange cloud above the unlit part of the Moon, which unexpectedly flared up in the sunlight. However, one should not count too heavily on the likelihood that such an event could have occurred in historical times. The odds are 1 in 100. Nevertheless, there is historical evidence that likely describes a collision with the Moon, observed from Earth with the naked eye. On the evening of June 25th, in the year 1188, English monks reported an unusual event that was later recorded in the Chronicle of Gervase of Canterbury, a reputable chronicler of political and cultural events of his time. After witnesses confirmed the truth of their accounts under oath, Gervase of Canterbury, 1141, around the 12th century, an English chronicler who composed a chronicle describing the period from 1100 to 1199, notes, immediately after the new moon, the horns of the lunar crescent, as usual in this phase, were turned eastward. Suddenly, the upper horn split into two, and from the gap between them, a blazing torch suddenly shot out, spewing fire, hot coals, and sparks. Astronomers de Rol, Mulholland, and A. Deining calculated that, as a result of the impact on the lunar surface, a cloud of dust could rise above it, very similar in appearance to the description given by the Canterbury monks. If the collision occurred only 800 years ago, the crater should still be visible today. Due to the lack of air and water, erosion on the Moon occurs extremely slowly, so even small craters aged several billion years have been relatively well preserved. Based on Gervase's description, it is possible to pinpoint the area on the Moon to which the evidence of the collision relates, producing rays, narrow long strips of fine dust ejected during the explosion. Such rays accompany the youngest craters on the Moon, such as Aristarchus, Copernicus, and Kepler. However, while lunar craters can withstand erosion, these exceptionally thin rays cannot, and over time, even micrometeorites falling on the surface, the finest dust settling from space, gradually erase and cover the rays, leading to their disappearance. Thus, the rays are a distinctive sign of a recent collision. Meteorite specialist Jack Harding discovered a very fresh, seemingly young crater with a well-defined ray system in the very area of the Moon indicated by the Canterbury monks. The crater has been named Giordano Bruno in honor of the monk scientist who lived in the 16th century and asserted that there are countless worlds, many of which are inhabited. For this and other crimes, he was burned alive in the year 1600. Confirmation of another kind was found by Lecolam and Mulholland. When an object crashes into the Moon at high speed, it causes the Moon to wobble slightly. Eventually, These oscillations fade, but not over such a short period as 8 centuries. Such vibrations can be detected using laser rangefinders. During the Apollo project, astronauts placed special mirrors, called laser retroreflectors, at several points on the moon. A retroreflector is a light-reflecting device that reflects incoming light exactly back in the opposite direction, regardless of where the light beam came from. When a laser beam directed from Earth strikes such a mirror and returns, the time it takes to travel to and from can be measured with astonishing accuracy. By multiplying this time by the speed of light, we can determine the distance to the moon at the moment of measurement with equal precision. Such measurements, conducted over several years, revealed that the moon wobbles with a period of about 3 years and an amplitude of approximately 3 meters, which does not contradict the hypothesis that the Giordano Bruno crater was formed less than 1,000 years ago. Today, the hypothesis that the Giordano Bruno crater was formed in the 12th century can be considered definitively disproven. Firstly, on June 25th, in the year 1188, the moon was still too close to the sun for anything to be seen on it at all. It was just over a day after the new moon. Secondly, an analysis conducted by Paul Vittoris from the University of Arizona shows that in a collision resulting in the formation of a crater on the moon measuring 22 kilometers, about 10 million tons of debris would have been ejected toward Earth. This would have led to extremely intense meteor showers that would have been observed for a week, starting from the day after the collision. Nothing of the sort is mentioned in any chronicle of that time. Thirdly, the same Vittoris reanalyzed the data from laser ranging of the moon and demonstrated that the cause of the noted small oscillations lies in the liquid interior of the moon. Finally, according to the latest data obtained from the Clementine spacecraft, which mapped the surface, the Giordano Bruno crater, while being the youngest crater of its size on the moon, is still over 800 years old. News from Sky and Telescope magazine on March 16, 2001. All this evidence is indirect and obtained through reasoning. As I have already said, the chances of such an event occurring in historical times are very low. However, the evidence presented at least gives us pause for thought. Like the Tunguska meteorite and the Ryazan crater, they confirm that large but not catastrophic collisions occurred not only in the early history of the solar system. The fact that only a few lunar craters have a developed system of rays indicates that even the surface of the moon is to some extent subject to erosion. On Mars, where erosion processes occur much more intensely, although there are many craters, as expected, there are virtually no craters with rays. By studying how craters overlap one another and other elements of lunar stratigraphy, we can reconstruct the sequence of collisions and flooding, among which the formation of the Giordano Bruno crater is likely the most recent event. Earth is very close to the moon. If the moon is pockmarked with impact craters, how did Earth escape a similar fate? Why are meteorite craters so rare? Perhaps comets and asteroids avoid falling on populated planets? They are unlikely to be so considerate. The only possible explanation is that impact craters form at roughly the same frequency on our planet as on the moon. However, on the airless and waterless moon, they are preserved practically forever, while on Earth, erosion gradually erases them or hides them beneath sedimentary rocks. Running water, wind-blown sand, and mountain building act slowly, but over millions and billions of years, they can completely smooth even very large scars. The surface of any moon or planet is subject to external influences, such as cosmic collisions, and internal ones, such as earthquakes. These can be short-lived catastrophes, like volcanic eruptions, or painfully slow processes, like erosion caused by wind-blown sand. There is no universal answer to the question of which influences dominate, external or internal, rare but destructive events, or constant and subtle phenomena. On the Moon, external catastrophic events predominate, while on Earth, internal, slowly occurring processes do. Mars represents an intermediate case. Between the orbits of Mars and Jupiter lie countless asteroids, tiny terrestrial-type planets. In the solar system, we distinguish between terrestrial group planets, which are poor in hydrogen and have solid surfaces, and gas giants of the Jupiter group, which have hydrogen-rich atmospheres beneath which a solid surface cannot be detected. By classifying asteroids as terrestrial-type planets, Sagan points out that they are compositionally similar to the terrestrial group. The largest among them reach several hundred kilometers in diameter. Many have elongated shapes and tumble as they move through space. In some cases, two or more asteroids appear to be moving along very closely spaced orbits. Asteroid collisions occur frequently, and the resulting fragments may randomly encounter Earth and fall to its surface as meteorites, so fragments of distant worlds are stored in the exhibits and reserves of our museums. The asteroid belt is a gigantic mill grinding fragments into dust. The largest fragments of asteroids, along with comets, are responsible for the appearance of fresh craters on the surfaces of planets. It is possible that the asteroid belt formed in a location where a planet could not form due to the tidal effects of the nearby giant Jupiter, or perhaps it is the remnants of a planet that exploded. The latter, however, seems incredible, as no scientist on Earth knows how a planet could explode. And perhaps that is not such a bad thing. Saturn's rings bear some resemblance to the asteroid belt. Trillions of tiny icy satellites orbit the planet. They may be fragments that the gravity of Saturn did not allow to coalesce into a large moon close to the planet, or remnants of a moon that was too close to Saturn and was torn apart by tidal forces. According to another hypothesis, there may be a dynamic equilibrium between the material ejected from Saturn's moon Titan and the material falling into the planet's atmosphere. Jupiter and Uranus also have ring systems, which were only recently discovered and are nearly invisible from Earth. Does Neptune have rings? This is a pressing question for modern planetologists. Ground observations of star occultations by Neptune in the early to mid-80s provided the first evidence of rings, and the Voyager spacecraft discovered a system of 5 rings around Neptune in 1989, named after famous astronomers: Adams, Sella, Oberon, Lassia, and A. Rog. The outer Adams ring contains 3 arcs, or arcs, known as liberty, equality, and brotherhood. It is likely that rings are an invariable attribute of Jupiter-type planets. Psychiatrist Immanuel Velikovsky, in his popular book Worlds in Collision, published in 1950, describes grand collisions that planets have experienced recently, from Saturn to Venus. According to his hypothesis, a planetary mass object that Velikovsky calls a comet was somehow ejected from the Jupiter system about 3,500 years ago. This object entered the inner regions of the solar system and experienced multiple collisions with Earth and Mars. One such random collision caused the Red Sea to part, allowing Moses to lead the children of Israel out of Pharaoh's land. Another halted the planet's rotation during the command of Joshua. According to Velikovsky, these collisions also caused powerful volcanic eruptions and floods. As far as I know, the first attempt to explain historical events through the invasion of a comet without relying on mysticism was made by Edmund Halley, who suggested that the global flood occurred due to a comet impact. He believed that after this complex game of interplanetary billiards, the comet settled into a stable, nearly circular orbit, becoming the planet Venus, which, according to Velikovsky, did not exist before that. I have already explained in detail that all these notions are almost entirely erroneous. Astronomers do not deny the possibility of large collisions, but they do not allow for such collisions to have happened in the recent past. In no model of the solar system can the sizes of planets be shown to scale with their orbits, as the planets would be nearly impossible to see. They would be so small. Today, more than 50 scaled models of the solar system have been created worldwide. In them, the Sun and the planets, as well as the distances between them, are shown to scale. In the most popular scale of 1 to 1 billion, the Sun has a diameter of 1 meter 40 centimeters. Earth is 1 centimeter 3 millimeters, and the distance to Pluto is 6 kilometers. If the planets are represented to scale as specks of dust, it becomes immediately clear that the probability of a single comet colliding with Earth over a span of several thousand years is extremely low. Moreover, Venus has a rocky metallic composition and is visible in hydrogen, while Jupiter, from which, according to Velikovsky, it originated, is almost entirely made of hydrogen. There are no energy sources capable of ejecting a comet or planet from Jupiter. Even if such an object were to pass near Earth, it would not be able to stop its rotation, let alone cause it to rotate again at a speed of one rotation every 24 hours. There is no geological evidence of increased volcanic activity or floods 3,500 years ago. Venus is mentioned in Mesopotamian inscriptions made before. According to Velikovsky, it transformed from a comet into a planet. It is utterly implausible that an object with such an elongated orbit could quickly transition to a nearly perfectly circular orbit like that of modern Venus. There are plenty of objections to be raised. Many hypotheses proposed by both scientists and amateurs have proven to be erroneous, but science corrects its own mistakes. To gain acceptance, all new ideas must undergo rigorous scrutiny of evidence. In Velikovsky's case, the worst part is not that his hypothesis is incorrect or contradicts well-established facts, but that some people who consider themselves scientists have tried to suppress his work. Science is built on free inquiry and serves it. Any hypothesis, no matter how strange it may seem, deserves to be considered on its merits. Banning inconvenient ideas is common in religion or politics, but this path does not lead to knowledge and has no place in scientific inquiry. We are not privy to know who will uncover new fundamental truths. Venus has nearly Earth-like mass, size, and density, making it 30 million times more massive than the largest known comets. As the closest planet to us, it has been regarded as Earth's sister for centuries. So what is the true nature of this sister planet? Could it be that there reigns a blessed eternal summer, slightly warmer than on Earth, since it is a bit closer to the Sun? Are there impact craters, or have they all been destroyed by erosion? Are there volcanoes, mountains, oceans, life? The first person to look at Venus through a telescope was Galileo in the year 1609. He saw a disk with absolutely no details. Galileo discovered that Venus changes phases, like the moon, from a thin crescent to a full disk, and the reason for these changes as well. Sometimes we see mostly the night side of Venus, and sometimes the day side predominates. This discovery, by the way, supported the theory that the Earth revolves around the Sun, not vice versa. The sizes of telescopes grew. Their resolution, the ability to distinguish fine details, increased. They were systematically directed at Venus, yet they showed no more than Galileo could see. Venus was shrouded in a thick layer of opaque clouds. When we look at the planet shining in the morning or evening sky, we see sunlight reflected off Venus's clouds. However, for centuries after their discovery, the chemical composition of the clouds remained completely unknown. The inability to discern anything on Venus led some scientists to the strange conclusion that its surface resembled a swamp, like that which existed on Earth during the Carboniferous period. The argument, if it can be called that, went something like this: I can't see anything on Venus. Why? Because it is completely hidden by clouds. What are these clouds made of? Water. And of course, why are the clouds on Venus thicker than those on Earth? Because there is more water there. But if there is more water in the clouds, there must also be more on the surface. What could such a wet surface be? A swamp. And if there is a swamp, why can't there be cicadas, dragonflies, and perhaps even dinosaurs on Venus? Observing Venus reveals absolutely nothing. The conclusion: there must be advanced life there. The faceless clouds of Venus reflected only our hopes and expectations. We are alive, and we conclude that life must be everywhere. But only careful collection and analysis of facts can answer the question: is this world inhabited? Venus chose not to accommodate our prejudices. The first real key to unraveling Venus's nature came from experiments with glass prisms and diffraction gratings, a flat surface on which thin parallel lines are drawn at equal intervals. When an intense stream of ordinary white light passes through a narrow slit and then through a prism or grating, it separates into the colors of the rainbow, forming a spectrum. The spectrum encompasses colors: violet, blue, green, yellow, orange, red, in order from high frequency to low. In English-speaking countries, it is customary to consider that there are 6 primary colors in a rainbow, as blue and light blue are not regarded as separate. Light is a wave process. Its frequency is the number of wave crests that reach a recording instrument, say, the retina of the eye, in a unit of time, such as a second. A higher frequency corresponds to higher energy radiation. It is called the spectrum of visible light, because all these colors are accessible to our vision. However, light is more than just that small section of the spectrum that we perceive. In the high-frequency range beyond violet lies the ultraviolet radiation region. This is real light that brings death to microbes. It is invisible to us, but easily detected by bees and photoelements. Beyond ultraviolet lies the X-ray region of the spectrum, and even further is gamma radiation. In the low-frequency range beyond red lies the infrared section of the spectrum. It was first discovered when a sensitive thermal sensor was placed in the invisible area beyond the red edge. The temperature increased, indicating that light did indeed reach the thermometer, although it was invisible to our eyes. Rattlesnakes and semiconductors with special impurities can sense infrared radiation very well. Beyond infrared lies a vast spectral range of radio waves. Between the infrared and radio ranges The microwave radiation area is usually distinguished, which is used for heating food in microwave ovens and helps to study the era of our universe's birth. All of this, from gamma radiation to radio waves, represents different but equally important types of light. All are used in astronomy, but due to the limited capabilities of our vision, we prefer the tiny rainbow range known as the spectrum of visible light. In 1844, philosopher Auguste Comte sought an example of knowledge that would forever remain hidden from us. He settled on the chemical composition of distant stars and planets, believing we would never visit them, and without samples of their substances, we would be forever deprived of the ability to know their composition. But just 3 years after Comte's death, it was discovered that spectra could be used to determine the chemical composition of distant objects. Auguste Comte died in 1857, and just 2 years later, in 1859, Kirchhoff and Bunsen discovered line spectra that could distinguish each chemical element. Molecules and chemical elements absorb light of various frequencies or colors, sometimes in the visible part of the spectrum, sometimes in other areas. In the spectrum of a planetary atmosphere, a single dark line corresponds to a narrow gap where light is absent because solar radiation passing through the air of another world is selectively absorbed by it. Each such line is produced by a specific type of molecule or atom. Each substance leaves its characteristic spectral signature. The composition of Venus's gas envelope can be determined from Earth at a distance of 60 million kilometers. We can predict the chemical composition of the Sun, where helium was first discovered and named after the Greek sun god Helios, as well as magnetic stars of type A, rich in europium, and distant galaxies studied through the combined light of billions of stars. Astronomical spectroscopy is an almost magical technique. It continues to amaze me. Auguste Comte chose an exceptionally poor example. If Venus were indeed seeping moisture, lines of water vapor would easily be detectable in its spectrum. However, spectroscopic studies conducted around 1920 at the Mount Wilson Observatory found no trace or even hint of water vapor above Venus's clouds, suggesting the existence of a dry, desert-like solid surface blanketed by clouds of fine silicate dust. Further investigations revealed a vast amount of carbon dioxide in the atmosphere, leading some scientists to speculate that all the water on the planet reacted with hydrocarbons, resulting in carbon dioxide. Thus, the surface of Venus represents a vast oil field, a sea of oil covering the entire planet. Others concluded that there is no water vapor above the clouds because these clouds are very cold, and all the water condenses into tiny droplets, which have a different set of spectral lines than water vapor. They suggested that the planet is completely submerged in water, except perhaps for random islands covered with limestone, like the White Cliffs of Dover. However, due to the enormous amount of carbon dioxide in the atmosphere, the sea cannot consist of ordinary water. The laws of physical chemistry state that it must be carbonated, suggesting that Venus is a vast ocean of sparkling water. The first hint of the true state of affairs was obtained not by analyzing spectra in the visible and near-infrared regions, but through studies in the radio range. A radio telescope works more like an exposure meter. It is like a camera. You point it at a fairly large section of the sky, and it registers how much energy comes from there to Earth at a specific radio frequency. We are already accustomed to radio signals transmitted by some forms of intelligent life, namely those that build television and radio stations. However, there are many other reasons why natural objects can emit radio waves. One of them is heating. And when in 1956, one of the first radio telescopes was directed toward Venus, it was found that it emits radio waves as if heated to an extremely high temperature. But the definitive confirmation that Venus's surface is incredibly hot came from Soviet spacecraft of the Venera series, which first penetrated the cloud cover and descended to the mysterious and inaccessible surface of the closest planet. It turned out that Venus is terrifyingly hot. No swamps, no oil fields, no oceans of soda. In the absence of data, it is so easy to make mistakes. When I look at a friend, I see her thanks to sunlight, or, for instance, incandescent light. Light rays scatter off her and enter my eye. However, ancient thinkers, even great ones like Euclid, believed that we see through special rays emitted by our eyes that seem to touch the observed objects and actively interact with them. This natural view persists, although it does not agree with the invisibility of objects in a dark room. Today, we connect lasers, photoelements, or radio transmitters with radio telescopes, and in this way, we can actively interact with distant objects using light. In radar astronomy, radio waves are sent down from a radio telescope on Earth and reflected back. On many long wavelengths, the clouds of Venus's atmosphere are completely transparent to radio radiation. In areas where the surface is uneven, the radiation is absorbed or scattered in different directions. Such areas appear dark to radio waves. Tracking the movement of surface features during Venus's rotation allowed us to reliably determine the length of a day on the planet, the time it takes Venus to complete one rotation on its axis. It turned out that Venus takes 243 Earth days to complete one rotation relative to the stars, and it rotates in the opposite direction to the rotation of all the planets in the inner solar system. As a result, the sun rises in the west and sets in the east here, and between two sunrises, 118 Earth days pass. Additionally, during moments of maximum proximity to Earth, Venus always turns towards us almost exactly with the same side of its surface. Although this synchronized rotation with Earth was caused by the gravity of our planet, it did not happen suddenly. Venus is only a few thousand years old, and its age should be similar to that of all other objects in the inner part of the solar system. Radar images of Venus were obtained both by ground-based radio telescopes and by the spacecraft Pioneer Venus, which orbited the planet. The radar mapping of most of the northern hemisphere of Venus was carried out in 1983 by the Soviet stations Venus 15 and Venus 16. More detailed radio images were obtained by the American spacecraft Magellan, which operated in orbit around Venus from 1990 to 1994. In addition to radar maps covering more than 98% of the planet's surface, Magellan also created a gravity map encompassing 95% of the surface. These maps clearly show signs of impact craters, both small and large. The number of craters on Venus is roughly the same as that on the lunar highlands, which further confirms that the planet is very old. However, the Venusian craters are not deep at all, as if the rocks have flowed over long periods of time under the influence of high temperatures, smoothing the terrain like oil or clay. There are enormous plateaus here, twice the height of the Tibetan Plateau, vast rift valleys, possibly gigantic volcanoes, and mountains comparable in height to Everest. Now, we can see this world, previously completely hidden from us by clouds. Its details have been explored for the first time using radar and spacecraft. The temperature on the surface of Venus, according to radio-astronomical observations confirmed by direct measurements from spacecraft, is around 480 degrees Celsius, which is hotter than the hottest kitchen oven. The atmospheric pressure at the surface reaches 90 atmospheres, which is 90 times greater than that on Earth, and corresponds to the pressure of water at a depth of 1 kilometer. To survive long enough on Venus, a spacecraft must be designed like a deep-sea submersible and must also be well-cooled. More than a dozen spacecraft from the Soviet Union and the United States have entered Venus's dense atmosphere and penetrated through the clouds. Some of them managed to survive on the surface for about an hour. During the successful American Pioneer Venus project from 1978 to 90, an orbital module and 4 atmospheric probes were deployed, 2 of which managed to operate for a short time under the harsh conditions on the surface of Venus. The creation of spacecraft for planetary exploration led to many unexpected new developments. One of them was the inclusion of a net flux radiometer among the instruments installed on the atmospheric probes of the Pioneer Venus station, which measured the amount of infrared energy going up and down in each layer of the Venusian atmosphere simultaneously. A durable window, transparent in the infrared range, had to be manufactured for the instrument. For this purpose, a diamond weighing 13.5 carats was imported. The contractor had to pay a customs duty of $12,000, but eventually, the American customs decided that after the launch to Venus, the stone could no longer be considered a commodity on Earth, and the money was returned to the manufacturer. 2 Soviet Venus spacecraft transmitted images from there. Let us follow in the footsteps of the pioneering missions and visit another world. Venus 9 and Venus 10 transmitted the first black and white images of the surface of Venus. The first color images were obtained by the Venus 13 and Venus 14 spacecraft in 1982. In ordinary visible light, one can observe the pale yellow clouds of Venus. But, as Galileo first noted, there is almost nothing for the eye to rest upon. However, cameras operating in the ultraviolet range reveal a delicate, complex system of swirling winds in the upper layers of the atmosphere, blowing at speeds of about 100 meters per second. 96% of the atmosphere of Venus consists of carbon dioxide, with trace amounts of nitrogen, water vapor, argon, carbon monoxide, and other gases. But the concentration of hydrocarbons and carbohydrates does not exceed 1/10 of a part per million. The clouds of Venus, it turned out, are primarily a concentrated solution of sulfuric acid. There are also small amounts of hydrochloric and hydrofluoric acid. Even the upper cold layers of Venus turn out to be a completely dreadful place. Above the visible cloud layer, at an altitude of about 70 kilometers from the surface, a haze of tiny particles always hangs. At 60 kilometers, we dive into the clouds to find ourselves surrounded by droplets of concentrated sulfuric acid. As we descend, they grow larger. In the lower layers of the atmosphere, there are traces of the corrosive gas sulfur dioxide, SO2. Rising above the clouds, it undergoes the degrading effects of ultraviolet radiation from the sun and reacts with water to form sulfuric acid, which condenses into tiny droplets, settles, and at lower altitudes, due to heating, breaks down again into SO2 and water, completing the cycle. Sulfuric acid rains constantly fall across Venus, but no drop ever reaches the surface of the planet. The yellow-gray mist extends up to an altitude of 45 kilometers above the surface, and upon reaching this height, we find ourselves in a dense but crystal-clear medium. However, the atmospheric pressure is so great that it is impossible to see the surface. Sunlight, scattered by molecules in the atmosphere, completely hides it from view. There is no dust, no clouds. The planet's gas envelope becomes tangible. A considerable amount of sunlight penetrates through the clouds above, no less than on Earth on a cloudy day. The scorching heat, destructive pressure, toxic gases, and eerie reddish light make Venus resemble not the goddess of love, but rather an embodiment of the underworld. As far as we can judge, in some places, the surface is covered with randomly scattered, somewhat arranged rock fragments, a hostile, barren landscape occasionally diversified by the ruins of abandoned spacecraft from a distant planet. Completely indistinguishable even through the thick, poisonous cloud atmosphere. It is highly unlikely that anything alive could exist in such a dreadful place. Even an organism vastly different from us would have its organic and any conceivable biological molecules simply torn apart here. But let us be lenient and imagine that intelligent life did arise on such a planet. Would this life be able to create science? The development of science on Earth was based on observations of the patterns of movement of stars and planets, but Venus is completely shrouded in clouds. Night lasts about 59 Earth days. However, from the surface of Venus, you cannot see any objects of the astronomical universe in the sky. Not even the sun is visible during the day. Its light is scattered across the sky. As in the clouds, one sees only a uniform diffuse glow. If a radio telescope were built on Venus, it could detect the sun, Earth, and other distant objects. The existence of stars could eventually be deduced from general principles of physics, but these would be purely theoretical constructs. Sometimes I wonder what the reaction of intelligent beings on Venus would be if, having learned to fly in the dense atmosphere, they were to penetrate through the mysterious veil of clouds, rise above them at an altitude of 45 kilometers, and see the magnificent universe for the first time, the sun, planets, and stars. Astrophysicist and science popularizer, science fiction writer Boris Stern, in his novel Ice Shell from 2018, explored in detail how scientific knowledge could develop under similar conditions in a civilization at the bottom of the icy ocean of Jupiter's moon Europa. Venus provides us with an example of all planetary catastrophes. It is now clear that the high surface temperature is a consequence of a powerful greenhouse effect. Sunlight passes through the atmosphere and clouds of Venus, which are translucent to visible light, and reaches the surface. The heated surface attempts to radiate heat into space. Since Venus is much cooler than the Sun, it emits radiation primarily in the infrared range rather than in the visible spectrum. However, carbon dioxide and water vapor in Venus's atmosphere almost perfectly absorb infrared radiation. Solar heat becomes trapped, and the surface temperature rises until the small fraction of infrared radiation that manages to seep through the thick atmosphere balances the sunlight absorbed by the lower layers of the atmosphere and the surface. Currently, there remains some uncertainty in estimating the water vapor content on Venus. A gas chromatograph on the Pioneer Venus probe estimated the water content in the lower layers of the atmosphere at a few tenths of a percent. On the other hand, infrared measurements from the Soviet spacecraft Venus 11 and Venus 12 give a figure of about 0.01%. If we accept the first value as true, then carbon dioxide and water vapor are more than sufficient to retain almost all thermal radiation from the surface and ensure a temperature of around 480 degrees Celsius. If the second value is correct, and I believe it is more reliable, carbon dioxide and water vapor could only maintain a surface temperature of 380 degrees Celsius, and other components of the atmosphere would need to be involved to close the remaining infrared windows in the atmospheric greenhouse. A small amount of SO2 and HCl would be quite suitable for this role. All of them have been detected in Venus's atmosphere. Thus, the latest launches of American and Soviet spacecraft to Venus have confirmed that the greenhouse effect is indeed the cause of the high surface temperature. The neighboring world has appeared to us oppressive and unappealing, but we will return to Venus. It is still attractive in its own way. After all, the heroes of Greek and Scandinavian myths did not shy away from visits to the underworld. We have much to learn about our planet, which can be considered a paradise compared to this hellfire. The Egyptian Sphinx, half man, half lion, was built more than 5,500 years ago. Today, archaeologists date the construction of the Great Sphinx in Giza to the 26th century BCE, meaning it is estimated to be 4,600 years old. The Sphinx's nose was once sharp, but now its features are smoothed by the wind, which has carried sand from the desert for millennia and by rare rains. In New York, there is an obelisk brought from Egypt called Cleopatra's Needle. A second similar obelisk is located in London on the banks of the Thames. Both were built by Pharaoh Thutmose III in 1500 BCE and have no relation to Cleopatra, except that they stood in the capital of her kingdom, Alexandria. After centuries of standing in Central Park, they have nearly disappeared due to smog and industrial emissions, due to chemical erosion similar to that occurring in Venus's atmosphere. On Earth, erosion gradually erases information, but since it acts slowly, drop by drop, grain by grain, this process is difficult to notice. Large formations, such as mountain ranges, survive for tens of millions of years, smaller impact craters for hundreds of thousands, and large artificial structures for only a few thousand. More precisely, an impact crater 10 kilometers in diameter forms on Earth approximately once every 500,000 years. In a geologically stable area like Europe and North America, it will last about 300 million years. Smaller craters form more frequently and erode faster, especially in biologically active regions. In addition to slow, uniform processes, erosion and destruction are also aided by catastrophes of greater or lesser scale. The Sphinx has no nose. Some vandals shot it off. Some say it was the Turks. Others say it was Napoleon's soldiers. On Venus, on Earth, and everywhere in the solar system, there are traces of catastrophic destruction, half erased or hidden by slower, more uniform processes. On Earth, for example, atmospheric precipitation gathers into streams and rivers, creating enormous alluvial basins. On Mars, there are channels of ancient rivers, possibly emerging from beneath the surface. On its moons, there exists something like wide channels carved by flows of liquid sulfur. On Earth, in the upper layers of the Venusian atmosphere, powerful atmospheric processes develop on Jupiter. Sandstorms rage both on Earth and Mars. Lightning occurs on Jupiter, Venus, and our planet. The hypothesis of thunderstorm discharges on Venus, proposed in 1978, based on data from the Venus probes, apparently is not confirmed. On April 26, 1998, and June 24, 1999, the spacecraft Cassini, en route to Saturn, maneuvered near Venus. It failed to detect high-frequency signals characteristic of lightning. On Earth, during its close approach on August 8, 1999, Cassini's equipment recorded up to 70 lightning strikes per second. Volcanoes emit material into the atmosphere on Earth, and its internal geological processes slowly deform the surfaces of Venus and Mars, Ganymede, Europa, and of course, Earth. Glaciers, known for their slowness, produce large-scale transformations of landscapes on Earth and possibly on Mars. These processes do not necessarily proceed uniformly over time. Once, much of the European continent was hidden under ice. Several million years ago, the area where the city of Chicago now stands was buried under 3 kilometers of ice. On Mars, and throughout the solar system, we find formations that could not have arisen in our days. Terrains shaped hundreds of millions, billions of years ago, when the climate on the planets was likely completely different. There is another factor capable of changing the landscape and climate of Earth: intelligent life, which can significantly transform the environment. Like on Venus, a greenhouse effect created by carbon dioxide and water vapor operates on our planet. Without it, the global temperature would drop below the freezing point of water. Thanks to it, the oceans remain liquid, and life is possible on Earth. A slight greenhouse effect is a good thing. There is almost as much carbon dioxide on Earth as on Venus. It would be enough to create a pressure of 90 atmospheres. But this carbon dioxide is bound in the Earth's crust in the form of limestone and other carbonates. They are present in the atmosphere. If Earth were to move slightly closer to the Sun, the temperature would rise slightly. This would cause some CO2 to be released from the surface rocks and enhance the greenhouse effect, leading to further heating of the surface. Carbonates on the mountain surfaces would release more CO2, and it is possible that the greenhouse effect would spiral out of control. This, apparently, is what happened in the early history of Venus. Due to its proximity to the Sun, Venus serves as a warning of the catastrophe that could happen to a planet quite similar to ours. The primary sources of energy for modern industrial civilization are fossil fuels. We burn wood, oil, coal, and natural gas, and in doing so, we release combustion products into the air, primarily CO2. As a result, the carbon dioxide content in the Earth's atmosphere has significantly increased. We should be cautious not to allow an uncontrolled greenhouse effect. A global temperature rise of just 1 or 2 degrees could have catastrophic consequences. By burning coal, oil, and gasoline, we also release sulfuric acid into the atmosphere, and we already have, as on Venus, a light haze of sulfuric acid droplets lingering in the stratospheric layers. Our largest cities are polluted with toxic molecules. We do not understand what long-term consequences our current actions will lead to. Meanwhile, we have already altered the climate in the opposite direction. For hundreds of thousands of years, humans have burned and cleared forests, and the grazing of livestock has destroyed meadows. Slash and burn agriculture, industrial destruction of tropical forests, and trampling of pastures are still ongoing. But forests are darker than meadows, and meadows are darker than deserts. As a result, the amount of sunlight absorbed by the surface decreases. Thus, by changing land use patterns, we alter the surface temperature of our planet. Could this cooling increase the size of the icy polar cap, which, being very bright, would reflect even more solar radiation and thereby cause further cooling of the Earth, triggering a runaway albedo effect? Albedo is the fraction of sunlight that falls on a planet and is reflected back into space. The Earth's albedo is 30 to 35%. The rest of the sunlight is absorbed by the Earth's surface and is responsible for the average surface temperature. The wonderful planet Earth is our only home. Venus is too hot, Mars is too cold, and Earth is literally a paradise for people. After all, it is here that evolution gave rise to us, but our favorable climate may prove to be unstable. We are putting our poor planet through serious trials. Is there a danger of turning the Earth's environment into a Venusian hell or an icy Mars? The answer is simple. No one knows. We have only begun global climate research and comparisons of Earth with other worlds. These studies are funded sparingly and reluctantly. In our ignorance, we continue to alter and pollute the atmosphere, making the Earth's surface brighter, forgetting that the long-term consequences are largely unknown. Several million years ago, when the first human beings appeared, Earth was already a mature world, having lived 4,600,000,000 years since its catastrophe-rich youth. But it is we, humans, who have now become the new and possibly decisive factor. Our civilizations, our technologies, have given us the power to influence the climate. How will we use this power? Will we tolerate ignorance and complacency in matters that affect all humanity? Will we prefer immediate benefits over the well-being of Earth? Or will we learn to think on a larger timescale and, for the sake of our children and grandchildren, understand and protect the complex life-supporting system of our planet? Earth is a tiny and fragile world. It needs care. It is said that many years ago, a famous newspaper publisher sent a telegram to a well-known astronomer. Urgently telegraph 500 words. Is there life on Mars? The astronomer, with a sense of duty fulfilled, replied, "No one knows, no one knows, no one knows," and so on, 250 times. But no matter how insistently the experts signed their own ignorance, no one pays any attention to this. And from time to time, we have to listen to the dogmatic statements of those who are convinced they have logically proven the existence of life on Mars, and those who are convinced they have proven the opposite. Some desperately want there to be life on Mars, while others want it not to exist. Both camps allow for extremes. These passions harm the tolerance for uncertainty that is so important for science. It seems that many people simply wish to receive any definite answer that frees them from the heavy burden of holding two alternatives in their minds at once. Some scientists considered Mars to be habitable, relying on completely unfounded arguments, as was later proven. Others concluded that the planet was lifeless simply because the search for specific manifestations of life yielded negative or ambiguous results. This boulevard has often been sung for the red planet. Why Martians? Why so much intense thought and feverish fantasy dedicated to Martians rather than the inhabitants of Saturn or, say, Pluto? Because at first glance, Mars seems very similar to Earth. It is the closest planet whose surface we can observe. It has icy polar caps, white clouds drifting, fierce dust storms leading to seasonal changes, and even its days last 24 hours. More precisely, the duration of a solar day on Mars is 24 hours, 39 minutes, and 35 seconds. All of this creates the temptation to consider Mars a habitable planet. It has become a kind of mystical stage onto which we project our earthly hopes and fears. But prejudices, whether for or against, should not deceive us. Only facts are important, and they are still lacking. The real Mars is a remarkable world of the future. It is far more fascinating than our past conceptions of it. We have already reached Mars. We are following its sands. We have made real what was only a dream for centuries. No one would have believed in the last years of the 19th century that behind all that was happening on Earth, there were beings more advanced than humans, though just as mortal as they. That while humans were busy with their affairs, they were being observed, studied, perhaps as meticulously as a human microscopist studies the ephemeral creatures swarming and reproducing in a drop of water. With infinite complacency, humans scurried around the globe, occupied with their little affairs, confident in their power over matter. Perhaps the infusoria under the microscope behaves in the same way. No one thought that older worlds in the universe were a source of danger for humankind. The very thought of any life on them seemed unacceptable and incredible. It is amusing to recall some of the prevailing views of those days. The most that was allowed was that other people lived on Mars, probably less developed than we are, but in any case, ready to greet us as guests, bringing them enlightenment. Meanwhile, across the abyss of space, beings with highly developed, cold, unfeeling intellects, surpassing us as much as we surpass extinct animals, looked at Earth. And slowly, but surely, they were formulating their hostile plans against us. Thus begins the science fiction novel The War of the Worlds by Herbert Wells, written in 1897, which has become a classic of the genre and retains its allure to this day. In 1938, Orson Welles staged a radio version of Herbert Wells's novel, transferring the Martian invasion from England to the eastern United States, frightening millions of Americans who believed that Martians were indeed attacking. It was later shown that the scale of the reaction to this radio production was greatly exaggerated by newspaper reports and also by the first researcher of this incident, Professor Harley Cantrell. The newspapers were interested in undermining the reputation of radio as a new competing medium. Professor Cantrell made very serious distortions in processing the data, inflating the number of listeners and the intensity of their reaction. However, today, the idea of a widespread panic during the broadcast is considered a myth of American journalism. The fear and hope of finding life beyond Earth have accompanied us throughout history. For the last 100 years, our expectations have focused on one bright red dot in the Earth's sky. 3 years before the publication of The War of the Worlds, Boston resident Percival Lowell founded a large observatory where the most serious arguments in favor of the existence of life on Mars were obtained. A lifelong astronomy enthusiast, Lowell attended Harvard, was appointed to a semi-governmental diplomatic service in Korea, and led a life typical of a wealthy man. But until his death in 1916, he made significant contributions to our understanding of the nature of planetary evolution, and did much to discover the expansion of the universe and the discovery of the planet Pluto, named in his honor. The first 2 letters in the name Pluto coincide with the initials of Percival Lowell, and the symbol combining the spelling of these letters, PL, became the official designation of the planet. But Lowell's lifelong love was Mars. In 1870, he was struck by the report of Italian astronomer Giovanni Schiaparelli about canals on Mars. During the close approach of Mars to Earth, Schiaparelli observed a tangled network of single and double straight lines in various directions crossing the bright areas of the planet. Schiaparelli used the word canali, which in Italian means channels or waterways, but it was translated into English as canals, implying the involvement of an intelligent builder. A wave of enthusiasm for Mars swept across Europe and America, and Lowell became completely captivated by it. In 1992, Schiaparelli's eyesight began to deteriorate, and he announced that he would cease observing Mars. Lowell decided to continue the work. He wanted to create a first-class observation site, free from clouds or city lights, where visibility would be good. Astronomers refer to a calm atmosphere, which minimizes image shake in the telescope. Poor visibility is caused by small-scale turbulence in the atmosphere above the telescope, causing stars to twinkle. Lowell built his observatory far from home, on Mars Hill in Flagstaff, Arizona. Isaac Newton wrote that even if the theory of telescope creation could be fully realized, there would still be limitations that telescopes could not overcome. The air through which we look at the stars is in continuous motion. The only salvation is the quietest and calmest air, which is likely found at the tops of the highest mountains above the clouds. Today, on large telescopes, the negative influence of the atmosphere has been significantly overcome through adaptive optic systems. The state of the atmosphere in front of the telescope is continuously probed by a laser beam, and special actuators slightly deform the telescope's mirrors to precisely compensate for the distortions introduced by the atmosphere. He sketched details of the Martian surface, particularly hypnotizing himself to conduct such observations. It is not easy to spend long hours at the telescope on a frosty early morning. Visibility is often poor. The image of Mars is distorted and hazy, and you have to ignore what you see. Sometimes the image stabilizes, and for a moment, the details on the planet's disk become astonishingly clear. Then you must remember what you were fortunate enough to see and carefully transfer it to paper. You must cast aside all prejudices and impartially record the wonders of Mars. Percival Lowell's notebooks are filled with images of what he believed he saw: light and dark spots, a barely noticeable polar cap, and canals. The planet is crisscrossed with canals. Lowell believed he saw a world covered by a network of grand irrigation ditches carrying water from melting polar caps. Thirsty inhabitants of equatorial cities. He speculated that the planet was home to an older and wiser race, possibly vastly different from us. He supposed that seasonal changes in the dark areas were caused by the growth and wilting of vegetation. He assumed that Mars was very similar to Earth. In general, he assumed too much. Lowell envisioned Mars as an ancient, barren, and desiccated world, similar to Earth's deserts. His words had much in common with the southwestern United States, where his observatory was located. Mars appeared to him as a cool place, but still no less pleasant for life than southern England. The air is thin, but it contains enough oxygen for breathing. Water is rare, but a dense network of canals distributes life-giving moisture across the planet. As we now know, the most serious objections to Lowell's idea came from where they were least expected. In 1907, Alfred Russel Wallace, co-author of the theory of evolution and natural selection, was asked to review one of Lowell's books. The engineer-educated Wallace, although he believed, for example, in extrasensory perception, was extremely skeptical about the habitability of Mars. He showed that Lowell was mistaken in his calculations of the average temperature on Mars. It was not only inconsistent with the temperature of southern England, but it was almost everywhere below the freezing point of water, meaning that permafrost must lie beneath the surface. The air is much thinner than Lowell's calculations suggested. Craters should occur as frequently as on the Moon. And as for water in the canals, Wallace wrote that any attempt to make such modest water supplies, full of water canals, flow across the equator into another hemisphere through terrible deserts under a completely cloudless sky, as Mr. Lowell describes, would be more the work of a group of madmen than intelligent beings. It can be confidently stated that even 100 miles from the source, it is impossible to avoid evaporation or absorption of any drop of water. Wallace made this devastatingly accurate physical analysis at the age of 84. His conclusion was that life on Mars, which he understood to mean civil engineers engaged in hydraulics, is impossible. He refrained from commenting on microorganisms. Despite Wallace's criticism, and contrary to the fact that other astronomers, whose telescopes and observatories were just as good, could find no signs of the legendary canals, the image of Mars created by Lowell gained wide popularity among the public. It possessed the allure of myths as ancient as the Book of Genesis. To some extent, this appeal is related to the fact that the 19th century was an era of engineering wonders, particularly the era of constructing grand canals. The Suez Canal opened in 1869, the Corinth Canal in 1893, and the first vessel passed through the Panama Canal in 1914. In the United States, the construction of a lock system in the Great Lakes region was completed, including the freight canals of New York State and irrigation canals. If such grand projects could be accomplished by Europeans and Americans, then why couldn't Martians? Wasn't an older and wiser species capable of putting forth much greater effort in their brave struggle against the desiccation of the red planet? Today, we have sent reconnaissance probes into orbit around Mars, mapped its entire surface, and 2 automated laboratories have landed on the planet. By the beginning of 2019, 4 rovers, 5 stationary landing modules, and 13 orbital missions had successfully participated in Mars research. However, since Lowell's time, the fog concealing the mysteries of Mars, if they even exist, has only thickened. We have obtained images of Mars that are far more detailed than what Lowell could observe. We found no traces of the famed network of canals, not a single lock. Lowell, Schiaparelli, and others who engaged in visual observations under challenging conditions were mistaken, partly perhaps because they wanted to believe in the existence of life on Mars. The observation diaries of Percival Lowell reflect his continuous years of work at the telescope. They show that Lowell was well aware of the skepticism with which other astronomers regarded the reality of the canals. Behind the pages of the diaries, one sees a man convinced he has made an important discovery and disheartened that others still do not understand its significance. In a notebook from 1905, for example, there is a note dated January 21st. The double canals that can sometimes be discerned are undoubtedly real. Reading Lowell's diaries, I felt a distinctly uncomfortable sensation that he truly saw something. But what? When Paul Fox and I from Cornell compared Lowell's maps with the images transmitted from the orbit by Mariner 9, the resolution of individual photographs was 1,000 times greater than what Lowell's 24-inch refractor could provide on Earth. There were no practical disks between them, nothing in common. It was not that Lowell's eye merged disparate faint details on the Martian surface into straight lines. In the places where most canals were supposed to be, there were no dark spots or chains of craters. There were no details at all. But how then did he manage to draw the same canals year after year? And how did other astronomers, some of whom claim they did not study Lowell's maps in detail before conducting their own observations, manage to sketch the same canals? One of the most significant discoveries of Mariner 9 was the detection of changing bands and spots on the surface of Mars that varied with the seasons, many of which are associated with the circular mounds of impact craters. The cause is wind-blown dust, which creates patterns dependent on seasonal winds. However, the bands do not resemble canals and do not coincide with them in location, and none of them, individually, are large enough to be noticeable from Earth. It is unlikely that in the early 20th century, there were indeed formations on Mars that even remotely resembled Lowell's canals, and vanished without a trace as soon as detailed investigation became possible through spacecraft. The Martian canals appear to be the result of some strange malfunction in the combined work of hands, eyes, and brains, manifesting in humans under complex observational conditions, at least in some people. Many astronomers have tools and conditions for observation similar to those of Lowell, and have stated that there are no canals. But even this explanation is far from satisfactory, and I continue to be troubled by doubts that some significant detail in the problem of Martian canals remains undisclosed. Lowell always claimed that the correct shape of the canals is an infallible sign of their intelligent origin. This is certainly true. The only unresolved question is, from which side of the telescope was this intelligence situated? In the gentle light of the moon, Martians are kind and optimistic, even somewhat godlike, having nothing in common with the malevolent, dangerous beings depicted by Wells and Herbert in The War of the Worlds. Science fiction and Sunday newspaper supplements have delivered both of these portraits to the public's imagination. I remember as a child breathlessly reading the Martian novels of Edgar Rice Burroughs. Together with John Carter, a gentleman and adventurer from Virginia, I traveled to Barsoom, as Mars was called by its inhabitants. I followed a caravan of Tharks, eight-legged pack animals, sought the hand of the beautiful Dejah Thoris, Princess of Helium, and befriended Tars Tarkas, the selfless green warrior towering at 4 meters tall. I wandered among the spired cities and domes of Barsoom's pumping stations, across the blooming slopes of the heights of Nepenthe and the merciful Nepenthe, and on to the Surt, the Dining Mountains, the Melancholy, the peaks of the heights with their steep edges. Is it really conceivable to join John Carter in the Martian kingdom of helium? Can we embark on a daring scientific expedition one fine summer evening, along a road illuminated by the light of Barsoom's 2 swift moons? Even if all of Lowell's conclusions about Mars, including the existence of the infamous canals, are entirely unfounded, his description of the planet accomplished at least one useful thing. It made an entire generation of people, myself included, believe in the reality of planetary exploration and wonder whether we might one day fly to Mars ourselves. John Carter only needed to step out into a clear field, raise his hands, and become filled with passionate desire. I remember spending countless hours as a child wandering in the field, stretching out my hands, and appealing to what I believed to be Mars to take me there. Nothing came of it. I had to find another way. Like organisms, machines evolve. Rockets, like those powered by black powder, first appeared in China, where they were used for ceremonial purposes and to adorn festivities. Introduced to Europe around the 14th century, they found military applications. By the end of the 19th century, a school teacher from Russia, Konstantin Tsiolkovsky, proposed using them for interplanetary travel. American scientist Robert Goddard was the first to seriously work on the problem of high-altitude flights. According to a U.S. aviation historian, black powder and festive lights, that is, rockets, appeared in Russia in the 12th century. In 1613, Polish military architect Sidor provided designs for multi-stage rockets in his work Manual of Weapon Production. And in 1649, French poet and writer Cyrano de Bergerac wrote in Other Worlds, or the State of the Moon and its Inhabitants, about a multi-stage transport rocket used for flights from Earth to the Moon. Despite this, traditions attribute priority in these matters to Konstantin Tsiolkovsky. He never created his own high-altitude rockets. Many claim priority in launching the V-2 rocket with a liquid rocket engine, which was not a continuation of Goddard's work. The Germans followed their own path, using the idea of their compatriot Oberth for the V-2. During World War II, almost all of Goddard's advancements were realized in the German military rocket V-2, culminating in the launch of the two-stage V-2 WAC Corporal rocket in 1948, which reached an unprecedented height of 400 kilometers for that time. In the 1950s, engineering developments under the leadership of Sergei Korolev in the Soviet Union and Wernher von Braun in the United States, funded for the purpose of creating systems for delivering weapons of mass destruction, led to the launch of the first artificial satellites. Further progress was rapid. Manned orbital flights, lunar flybys, and the first human landing on its surface, sending automatic interplanetary stations to the planets of the solar system and beyond. Many countries have already launched their own spacecraft, including the United Kingdom, France, Canada, Japan, and China, the country where rockets were first invented. Countries with their own technologies for creating space launch vehicles are considered spacefaring nations. These include, in order of entry, the USSR, the USA, France, Japan, China, the United Kingdom, India, Israel, Iran, and North Korea. Canada does not have its own launch vehicles. Since 1975, European countries have united their space programs under the European Space Agency. With the development of private space travel, it has become increasingly difficult to determine the national affiliation of launches. For instance, in 2018, the Electron rocket was launched from New Zealand by a local company that is owned by an American. Above all, space rockets, as Lowell dreamed in his youth while reading in LS and listening to lectures by Percival Lowell, were meant to serve as orbital scientific stations for observing the Earth from great heights and probes for searching for life on Mars. Both of these dreams have found their realization today. Imagine yourself as an alien from some completely foreign planet approaching Earth, unaware of what awaits you. The closer the planet, the clearer the view, the more distinct the increasingly subtle details become. Is it habitable? At what moment can you answer this question? If there are intelligent beings here, they have likely created engineering structures with contrasting elements measuring several kilometers in size. These structures are easily discernible when optical systems and the distance to Earth provide kilometer resolution. However, at this level of detail, Earth appears completely desolate. In places we call Washington, New York, and Boston, Moscow, London, Paris, Berlin, Tokyo, and Beijing, there are no signs of life. Are they intelligent? If there are intelligent beings on Earth, they have not significantly altered its landscape, nor created a regular geometric pattern noticeable at kilometer resolution. But when we increase the resolution tenfold and begin to see details around 100 meters in size, the situation changes. Many places on Earth seem to crystallize, suddenly revealing a complex pattern of squares and rectangles, straight lines, and circles. This is the engineering artifact of intelligent life. Roads, highways, canals, and agricultural lands, urban streets, a pattern revealing two related human tendencies: Euclidean geometry and the defense of their territory. At this scale, intelligent life can be detected in Boston, Washington, and New York. And at 10 meters of resolution, it becomes clear just how much the landscape has actually been transformed. Humans have worked hard. This is evident in the images of the planet's daytime surface. In twilight and at night, other things become visible. The flares of oil wells in Libya and the Persian Gulf, deep-sea lighting used by the Japanese fishing fleet to catch squid, the lights of large cities. And if during the daytime we increase the resolution to see objects about 1 meter in size, we can finally discern individual living organisms: whales, cows, flamingos, and people. On Earth, intelligent life primarily manifests itself in the geometric precision of the structures it creates. If Lowell's network of canals truly existed, the presence of intelligent beings on Mars would be almost inevitable. Geometric precision is not always a consequence of intelligent activity. In the previous chapter, Sagan notes that Kepler mistakenly attributed the correct circular shape of lunar craters to intelligence. Numerous straight grooves have been discovered on Jupiter's moon Europa, clearly visible at a resolution of around 200 meters. But the causes that created them appear to be entirely natural. For life to be identified on Mars through photographs, even those taken from orbit, it must significantly alter the planet's surface. Technical civilizations build canals, which should be easily detectable. But with the exception of one or two mysterious formations, nothing similar can be discerned in the abundance of details on the Martian surface in images obtained from unmanned spacecraft. Nevertheless, there is a wide range of other possibilities, from large animals and plants to microorganisms, fossil forms of life, and complete lifelessness of the planet, both now and in the past. Since Mars is farther from the Sun than Earth, temperatures here are significantly lower. The thin atmosphere consists mainly of carbon dioxide, with small amounts of molecular nitrogen and argon, and extremely minor traces of water vapor, oxygen, and ozone. Open bodies of water cannot exist on Mars, as the low atmospheric pressure cannot prevent even cold water from boiling. A negligible amount of liquid water may be contained in the pores and capillaries of the soil. The amount of oxygen is far less than what is required for human respiration, and there is so little ozone that the deadly ultraviolet radiation from the sun reaches the Martian surface unimpeded. Can any organism survive under such conditions? To answer this question, my colleagues and I many years ago created chambers in which we modeled Martian conditions based on the knowledge available at the time. We populated them with terrestrial microorganisms and began to observe whether at least some of them could survive. We called these chambers Mars jars. The temperature in them cycled within a typical Martian range, from just above the freezing point of water at noon to about -80 degrees Celsius before dawn. Without an oxygen atmosphere, it consisted mainly of carbon dioxide and water vapor. Ultraviolet lamps simulated harsh solar radiation. There was no liquid water, except for a very thin film moistening individual grains of sand. Some microbes froze and died on the very first night, showing no further signs of life. Others suffocated and perished from lack of oxygen, while some died of thirst or ultraviolet radiation. But there was always a sufficient number of species of terrestrial microbes that did not require oxygen, which paused their life and activity when temperatures dropped too low, and which sheltered themselves from ultraviolet radiation under stones or beneath a thin layer of sand.